Nanjing, the capital of Jiangsu Province, is an ancient capital of the Six Dynasties with profound historical and cultural heritage, and a modern international metropolis that is friendly, livable, tolerant, and open. Nanjing University of Science and Technology, established in 1953, is located in the most beautiful Zhongshan Scenic Area of Nanjing. It is a national key university affiliated to the Ministry of Industry and Information Technology. Upholding the motto, dedication to truth and innovation, NJUST actively integrates into the country's manufacturing and network construction, the Yangtze River Delta region development, and other major national strategies and regional economic and social development. With the strategy of one university and 3 campuses, NJUST has been committed to multidisciplinary development on engineering, science, medicine, human sciences, management, economics, and law. As a key university of 211 Project, a member of 985 Innovation Platform, and a double first-class construction universities and disciplines, NJUST has been dedicated to mounting up to the plateau and peak of superior diversified disciplines. The university has 4 disciplines ranking in the top 1% of ESI disciplines, with engineering is in the top 1,000th globally. The university has 15 academic colleges, more than 2,000 full-time faculty members, 20 academicians, around 30,000 students, including 1,000 international students. Innovation is the key to the university's academic excellence. NJUST has more than 50 research platforms at the provincial and ministerial levels or above, and has undertaken a large number of major national scientific research tasks. NJUST has made fruitful innovation achievements on the way of continuous improvement in basic research capabilities and deepened coordination of industry, academia, and research. It has become an important base for scientific and technological innovation in China. NJUST has won 105 national scientific and technological awards, including 9 national first-class awards. As an academician of CAE, Professor Wang Zishan won the 2017 National Super Rim Award for Science and Technology. NJUST has been optimizing talent cultivation mode. The university devotes itself to cultivating innovative and elite talents with international competitiveness to lead the future. More than 230,000 NJUST alumni have graduated and been serving as innovative academic leaders, industrial elites, and pillars of governance for the country. NJUST students have won many awards in major events such as the Internet Plus Student Innovation and Entrepreneurship Competition, the Challenge Cup National Extracurricular Academic Science and Technology Competition, the Postgraduate Innovation and Practice Competition, ICANN International Contest of Innovation and International Collegiate Programming Contest. NJUST vigorously promotes the process of internationalization and has established close cooperation with more than 200 famous universities and research institutions abroad. With joint efforts, NJUST has established international cooperative bases such as Herbert Glader Institute of Nanoscience with KIT, Sino-French Engineer Institute with the University of Lorraine, Technology Innovation Support Center with the World Intellectual Property Organization, to carry out cultural exchanges and promote mutual understanding among civilizations. The university has set up research centers on the Kingdom of Saudi Arabia, the Republic of Belarus, Central and Eastern Europe. Stepping into NJUST campus, there is strong academic atmosphere, where elites and masters work side by side. Here stand the verdant and upright forest, the elegant Zixia Lake. Students embrace the vibrant campus life. Here, the pulse of Chinese history and culture can be touched. Students experience the speed of development of modern China. On the pursuit of truth and innovation, steps never stop. Explore the world of new knowledge and meet the bright future at NJUST.
In today's challenging environment, scientists and engineers need to accelerate discovery processes. CAMICA offers unique, high-performance analytical instruments to help them unveil the secrets of life and materials at the micro, nano, and even the atomic scale. Founded near Paris in 1929, CAMICA rapidly established its name by pioneering first electron probe.
Nanjing, the capital of Jiangsu province, is an ancient capital of the Six Dynasties with profound historical and cultural heritage, and a modern international metropolis that is friendly, livable, tolerant, and open. Nanjing University of Science and Technology, established in 1953, is located in the most beautiful Zhongshan scenic area of Nanjing. It is a national key university affiliated to the Ministry of Industry and Information Technology. Upholding the motto, dedication to truth and innovation, NJUST actively integrates into the country's manufacturing and network construction, the Yangtze River Delta region development, and other major national strategies and regional economic and social development. With the strategy of one university and 3 campuses, NJUST has been committed to multidisciplinary development on engineering, science, medicine, human sciences, management, economics, and law. As a key university of 211 Project, a member of 985 Innovation Platform, and a double first-class construction universities and disciplines, NJUST has been dedicated to mounting up to the plateau and peak of superior diversified disciplines. The university has 4 disciplines ranking in the top 1% of ESI disciplines, with engineering is in the top 1,000th globally. The university has 15 academic colleges, more than 2,000 full-time faculty members, 20 academicians, around 30,000 students, including 1,000 international students. Innovation is the key to the university's academic excellence. NJUST has more than 50 research platforms at the provincial and ministerial levels or above, and has undertaken a large number of major national scientific research tasks. NJUST has made fruitful innovation achievements on the way of continuous improvement in basic research capabilities and deepened coordination of industry, academia, and research. It has become an important base for scientific and technological innovation in China. NJUST has won 105 national scientific and technological awards, including 9 national first-class awards. As an academician of CAE, Professor Wang Zishan won the 2017 National Super Rim Award for Science and Technology. NJUST has been optimizing talent cultivation mode. the university devotes itself to cultivating innovative and elite talents with international competitiveness to lead the future. More than 230,000 NJUST alumni have graduated and been serving as innovative academic leaders, industrial elites, and pillars of governance for the country. NJUST students have won many awards in major events such as the Internet Plus Student Innovation and Entrepreneurship Competition, the Challenge Cup National Extracurricular Academic Science and Technology Competition, the Postgraduate Innovation and Practice Competition, ICANN International Contest of Innovation and International Collegiate Programming Contest. NJUST vigorously promotes the process of internationalization and has established close cooperation with more than 200 famous universities and research institutions abroad. With joint efforts, NJUST has established international cooperative bases such as Herbert Glader Institute of Nanoscience with KIT, Sino-French Engineer Institute with the University of Lorraine, Technology Innovation Support Center with the World Intellectual Property Organization, to carry out cultural exchanges and promote mutual understanding among civilizations. The university has set up research centers on the Kingdom of Saudi Arabia, the Republic of Belarus, Central and Eastern Europe. Stepping into NJUST campus, there is strong academic atmosphere where elites and masters work side by side. Here stand the verdant and upright forest, the elegant Zixia Lake. Students embrace the vibrant campus life. Here, the pulse of Chinese history and culture can be touched. Students experience the speed of development of modern China. On the pursuit of truth and innovation, steps never stop.
Okay, welcome back, everybody. I'm hopeful that everybody can hear my sound. Can somebody say that I'm audible?
Yes,
We can hear you.
Fantastic. Okay. So I think we have one more minute. So let's give some more time for everybody to join back in. Hi, Richard. All right, it's exactly 10 o'clock. So I'll be starting the post-lunch session for today. And it's my honor to announce about the Muller Award members and Muller Award winner and the Best Poster Award winner. So this is one of the best part of best honor that we get as the Vice President of International Field Emission Society. So for those of you who may not know me, I'm Arun Devraj. I'm from Pacific Northwest National Laboratory. If you just to kind of give a broad introduction about what Muller Awards are, so Muller Award is the most prestigious award in the IFS community. It recognizes an emerging scientist for a recent or original work in the field, specifically in field emission, field ionization, or related phenomena. It includes, but not limited to, technique development, application, or theory development. Candidates to the Erwin Muller Outstanding Emerging Scientist Award must be PhD students or must have obtained their higher degree within 2 years preceding the APT&M meeting. And so from all the applicants, a list of finalists are selected from a Muller Award panel. And this Muller Award panel is selected to be to represent a portion, a significant broad section of IFS membership. So if you were attending the live Muller Award presentations, you probably you heard the Muller Award committee introduce themselves. The committee members this year were Sandra Taylor from PNNL, Tong Lee from Ruhr University Bochum, Catherine Rice from Chemica, Matthias Tuvander from Chalmers University, and Stefan Gristel from ETH Zurich. So the candidates are actually, initially they submit a return package, which is an extensive package. And then the return application is evaluated based on 4 different criteria. So the first is the scientific quality of the paper and relevance to the field of IFS community. And then the novelty, the quality of the writing of the paper, and track record of the candidate. Based on that, a selection of finalists are shortlisted, and those finalists, you heard from those finalists during the oral presentation. And during the oral presentation also, if you saw, the Muller Award committee got to ask specific questions, both just after their presentation and at the end of the competition. So there was a lot of interesting discussions between the candidates and the Muller Award committee members. And after the presentation, their scientific quality of the presentation, novelty, quality of the writing and the presentation, and how they handled question, all of these basically factored into the decision that was made by the Muller Award committee. So this year, a collection of fantastic 8 early career researchers essentially applied for this Muller Award competition this year. There were Renel Dubusque, Martin Mayer, Florent Exterior, Hina Kanchandani, Olha Nakochena, Jit Sarkar, Meherpat Monajim, Mengwei He. So, and you heard from 5 of them on the initial, the first day, or during the Muller Award competition. And the winner this year is selected by the Muller Award committee is Martin Mayer for his work on probing hydrogen contributions inherent to APT analysis of broad significance to IFS. According to the committee, his novel observations of energy deficits for hydrogen species could enable us to deduce contributions from the material versus from the chamber, which can be really big for a variety of material systems. Obviously, the competition was very, very tight, very, very tough, and they deliberated for many hours to come up to this conclusion. One notable runner-up that they would like to mention was Renel Dubusque. Her work on probing nanoscale chemical heterogeneity and inclusions within minerals presented new models of relevance to understanding material rheology that could also be applied across various material science topics. So congratulations to Martin Mayer for being the winner of the Erwin Muller Award this year. If he is here, really congratulations. And then I also have the honor of announcing the winner of the Best Poster Award. Professor Gangsha and a group of local organizing committee judged all the posters. Again, they mentioned that the quality of all the posters were really awesome. And it was a tough decision for them also. And they particularly tried to focus on encouraging early career researchers who are basically the future of IFS and our community. And the winner of the best poster competition is Dr. Shuo Zhang and his poster was on approaches to prepare frozen hydrated nanoscale needles for cryogenic high resolution characterization. So really congratulations to Dr. Shuo Zhang also, and also our Erwin Muller awardee, Martin Mayer. Thank you. Professor Gangsha, are you here? If yes, I can hand it over to you because we have some more time before the session starts.
Okay, I'm here. Yes. And thank you for making this announcement. It's always good results, It's I think all the works presented during the conference, also in particular the Mueller computations, are excellent. Also, when we review all the abstracts, the review work was done by the organization committees, and we are all impressed by the quality of abstracts submitted to this conference. So that's the reason we make a big effort to incorporate all the talks, also the posters into the programs. And certainly, I think the 4 days intensive work deserve, this type of a platform to give these presentations. So we are more presentations to come this afternoon. I hope everyone still enjoy it. And all the talks and the presentations is really updated the new research development and progress made in this field. So hopefully everyone enjoyed and keep to actively to get involved. So Peter, I know you will talk soon. Very nice to see you, Peter Pfeffer. Good. Okay, I think next session will be chaired by Professor Richard Forbes. He is a very, very senior member in this community. And so I will hand the speaker to Richard.
Okay, shall we wait to the official time?
Yes, it would be better to work to the official time. We still have 5 minutes. Okay,
yes,
that's good. Yes. Okay. So yeah, so this year I think really we accommodated a lot of the talks. It's about 80 regular talks. Also, there are 5 Mueller Award presentations. There are 9 invited talks. Also, there are 21 posters. That's really great. And so I really want to thank everyone, not only the speakers, also the chairs, the session chairs. They really make a great contributions to help us to organize, make the program running. So far, I think it's running all smoothly, and I would like to thank everyone on behalf of our organization committees, also our teams. Yeah. Okay, I think I can stop now.
Okay, so we'll have to sit quietly for about 5 minutes.
So meanwhile, I can probably continue talking about the Muller Award applicants. I will strongly encourage our IFIS community across the world who are attending here to for the next APT&M, which is supposed to be held at IMEC Belgium. Consider preparing your packages, especially if you are a senior PhD student or just graduated. It's a very good opportunity. Talk to your advisors or mentors, and then it's a prestigious competition, and even getting that opportunity to present and have that discussion is a great thing. So we hopefully will get more and more applicants as we go forward. So I just wanted to mention that. And and really all of our applicants did a fantastic job this year. Thank you.
Do you want to mention the standards?
Yes, fully agree.
Yeah. What is that, Richard?
Standards activity. We have done a little.
Sure. I think actually Professor Richard Forbes has been really helping us kind of forge ahead in atom probe standard terminology development. That might be something that that affects all of us in the community. So IFIS steering committee has been very interested in developing standardized terminologies and standard practices for atom probe community over many decades now. And there's been many discussions and things like that. And recently, we actually got together over the last 2 years, 3 years. There's been a lot more activity in that direction. We have a number of terms that were defined and incorporated now into a formal ISO TC 201 terminology documentation. And we have a formal definition of atom probe tomography, as well as many other terms. And we will be sharing it with the community. Hopefully, especially as the industries are adopting atom probe, we may have a lot of value of these standardized approaches. And at the 2023 APT&M meeting, there will be a dedicated standard session. If you are coming there, try to come in on Sunday, and the Sunday about the time then when the tutorials are there will be a dedicated standards discussion session. And if you are interested, please contact either myself or Professor Richard Forbes, and we can link you up into the process. That's enough.
Can I just say, we must be careful not to freeze bad practice into standards. So there's a certain amount of discussion as to what we actually want to do in defining terms. Where we got to so far is that, I don't know, about 10 terms have been put forward into one of the ISO committees, so then they become official. But this only happens every 5 years, so we now have a big time to sort of develop another set of terms. But in the meantime, they could go on the IFIT site, I assume. But there's quite a lot of work involved in getting agreement.
Yes. Thank you.
And so we need to plan this session in advance, not just allow it to happen.
Absolutely. Yep.
Okay, I think we might as well make a start. It's my pleasure to chair the 13th technical session, which is on instrument technique development. We have 5 talks, and I welcome the first speaker, who is Peter Felfer, who's working on compensating imaging distortions in a commercial reflectron type atom probe. You can probably see.
Should I start, or should I wait for a minute more?
Okay.
Just wondering if people, but I believe everyone would be in by now. Yeah, so let's just start then. Okay, so what I'm talking about today is essentially how can you do your own reconstructions using a reflectron, because obviously a lot of you, I believe it's more than, was it 60 or 80%? And I don't know. A lot of the instruments out there are reflectron type instruments, because obviously that gives us great mass resolving power. And the downside of that is that very many of us do not have access to doing your own reconstructions, at least not without having a lot of distortions in your reconstruction. So the question is, of course, how can I correct for those distortions so that I can go back to doing my own reconstructions? And the reason why we want to do that is because in my lab we have a lot of different instrumentation, some of it commercial, some of it home built. And so we want to really have our workflows the same for all the instruments, and have full flexibility with all of the workflows. And the reason why you want to do your own reconstructions, there's many different reasons. Yeah, sometimes things about your specimen in terms of properties that are not reflected in a reconstruction. So, for example, you have an oxide and a metal, and the oxide has a different density than the metal, and so you can work it into your reconstruction. Or you have correlative information about the shape of your specimen that you want to work in. Or something very trivial but very, very useful is that if you have maybe laser scanning artifacts, so you know that your voltage curve is not that great a representation of the radius evolution, but still better than just assuming a constant Schenck angle. You can just have a robust fit and get rid of those spikes in there. or you want to do something more fancy like shape-based reconstruction calibration and so on and so forth. Anyway, there's a lot of different cases why I might want to do that. And there's so many that I don't think it's reasonable to assume that anyone will ever come up with a program that covers all of the possible cases that you could have. But usually for a specific sample, it's relatively trivial to just change the reconstruction you have to something that accommodates whatever problem you're working on. Okay, so the question is then how do we do that? Oh, yeah, and if you want to do your own reconstructions, we've got protocols up on our GitHub. So on my GitHub on the Atom Probe Toolbox, there's workflows and there's a lot of code on how to do that. So it's relatively easy to do that. And if you look at that code, you will find there is one section called reflection image transformation. Proceed with caution right now if you use it, because it's not fully optimized yet, but I believe in a couple of weeks would have that finished, where you can let your data run through, and you see there is a LEAP 4000 XHR calibration grid file that you have to load in, and then it will do some kind of transform, and then you're good to go with your reconstruction. Okay, so how does a reflection work? Reflection relatively simply is an electrostatic mirror. So you have your specimen, your ions depart from your specimen, they fly into this electrostatic mirror bucket, which is a relatively sophisticated design. So here on the right side, I unfortunately don't have a photo of one of the LEAP's reflectrons, but this is a 3-dep reflectron. And you can see it's got some pretty sophisticated alignments of shape that make sure that your ions fly in predictable lines and get focused in the case of the LEAP, not in the case of the 3-dep, but in the case of the LEAP, they get focused. Thereby give you a time focusing, because ions that have more energy just fly deeper into the bucket. But you also get imaging distortions from that. So there is no reflection that gives you no wide angle reflection that just gives you a nice image. So how can we compensate for that? Yeah, well, if you have got any kind of imaging distortions using a barycentric affine transformation, so affine spaces are just simply spaces that have no notion of parallelity. Sorry, no notion of perpendicularity. They have a notion of parallelity, but not perpendicularity. And barycentric coordinates, local barycentric coordinates, can be used to have affine coordinates, where these shape deviations don't actually have any meaning, any geometric meaning per se. Long story short, what you do is you come up with a triangle mesh, give your detector coordinates some kind of coordinate in the triangle mesh relative to the triangle mesh, relative to the center of gravity of that triangle mesh. Then you know, or you should know, where those points of the triangle mesh are in both the undistorted and distorted space, and then it's pretty trivial to do a transform between those two spaces. You can also do that in 3D, which is not a topic of today's talk, but I did that a while ago, actually, making 3D meshes and transforming those between reconstructed and unreconstructed space, which makes it possible to transform objects into unreconstructed space for co-reconstruction. So if you want to do shape-based reconstructions, you can use that pretty well. And I haven't been able to use that ever since I had a reflector atom probe, and that really annoyed me. Yeah, so I had to come up with a method how to do that. Yeah, and how do we do that? Well, the easiest thing is if you have a mesh of known, if you have an object or an image of known shape, and you can assume that the reflection gives you constant imaging properties throughout the experiment. It doesn't change with voltage, it doesn't change with the specimen you have, and so on and so forth. You can just take that image, come up with a triangulated mesh, and then you have a known, you take an image of that grid, and then you have known locations in this plane here, where this shadow mask sits, and on a detector. Yeah, so you've implicitly gotten a correction for the distortions. And we just laser cut a grid with 250 micron pitch, put it into the counter electrode of the LEAP instrument, of our LEAP 4000. We've also sent it out to some other groups to do experiments on their other instruments. This is an older grid. This is 500 micron pitch, but it just gives a nicer photo than the 250 micron pitch. And then you have exactly this. So you have a shadow image of your grid. So you see the reference field distortion map that we got on the instrument. And then the procedure is, well, you could just do it manually and just put crosses at the intersections or something like that. But I prefer to come up with a algorithm that does it for us. So it's once you want to do it for multiple instruments, it's actually a relatively swift process. So it's a canny edge detection to find the edges, then a polynomial edge fitting to find the individual edges of the grid. Then you calculate the intersections, tessellate the mesh from that, extrapolate the mesh so that you also cover everything that's beyond the last struts of the mesh, and then you have a distortion mesh for your grid. And of course, you will know what the grid looked like originally, because you laser cut it, took a photo, took some measurements. And so the procedure is then relatively simple, because all you have to do is take the hit coordinates, transform them into pericentric coordinates, and then take the pericentric coordinates relative to this to the undistorted mesh, and transform back into Cartesian coordinates, into the Cartesian coordinates of this virtual detector space. Because if you remember the image from before, what you then have is an image that's kind of the image of what you would get if the detector would sit where the grid sits, right? So you can do the reconstruction then based on this. Of course, the reconstruction parameters, flight path length, and so on and so forth, are not physical flight path lengths, but just the flight path lengths relative to that imaging plane. And the good thing about that is that you get one calibration file per instrument. We've tried it out with a couple of instruments, and we see that the Reflectron image is actually rock solid. So props to Kamika then, I guess. The Reflectron image is rock solid for one instrument. We've also tried it on different instruments of the same class, so different LEAP 5000s. I don't think we have more than one LEAP 4000 file and one LEAP 3000 file, but we've tried it on at least two LEAP 5000s, and we saw no differences. But of course, we can now start sending our calibration electrode to anyone that's interested, possibly at some point. Just treat it nicely. Don't take the grid out, because now the grid's always at the same position. And then we can also compare instruments of the same class. But I'm fairly convinced that is completely uninteresting, because I don't think we're going to find many differences. But anyway, you can have one calibration file per instrument, which then means that for this procedure, you need no user input. All you do is you take your data, you let it run through the pericentric coordinate transform, which is saved for your instrument. And then you get the corrected field distortion, or you get the corrected hit coordinates, and then you can go on and do your reconstruction. We've also looked at the distortions you get in different instrument generations. So you can see here the LEAP 3000. This is the one in Leoben. And I apologize for the setup of the image, but I'm traveling, or I'm on a conference right now, and didn't have access to the latest version of this file. So it's it's rather inconsistent, unfortunately. Anyway, so this is LEAP 3000, LEAP 4000, LEAP 3000 and 4000 are fairly identical. And then there was a big leap forward, no pun intended, to the LEAP 5000 XR, where you can see the acceptance angle is a lot higher, so you can see a lot more of those grid lines than on the 3000 and 4000 reflectrons, and also some metrics are a little bit better, and I'll show that a little bit more in the next slide. Yeah, so if you compare the instrument generations, you'll see that LEAP 3000 and 4000, and The color coding, by the way, is the same for all three instruments, even though you don't see the one for the LEAP 5000, but it's always the same scale. So you can see area distortion just means the relation, the ratio of the highest of the area in one of those squares relative to the average, and you can see it gets a lot more even over the instrument generations. Same for the mesh skew angle, which is just the angle between in one of the corners, the bottom left corner. And the mesh anisotropy is the only thing. So that's the ratio of the long versus the short area of line of the square. This is the only thing that really has stayed the same, and this has gotten a little bit worse. But yeah, you get better coverage, better image area distortion, and so on and so forth. And honestly, it doesn't matter that as long as it's a coherent aberration, which means you can correct for it. It's actually fine. Any aberration is kind of fine. Okay, and this all is actually part of our Erlangen open source hardware tool chain, open source tool chain in anisotropic tomography. So we can now give you open source hardware designs, open control software. I think you saw the talk by Mirpat Monagem, who showed his open source control system. And this is specifically part of the open source analysis software. Yeah, so we can now offer pretty much end-to-end open source atom probe tomography, and obviously we're trying to also open up commercial instrumentation to as much usability as possible. Yeah. And with that, I want to say thank you to my group. So this is work that I've done together with Martina Heller, who's presented the poster on the new atom blend software that we also put out, and Benedict Ott. I would say thank for data collection to Martin Meyer at Oxford, who's collected the data from the LEAP 5000, and Michael Kladetz from Leoben, who's collected the LEAP 3000 and some LEAP 5000 data. And that's it for me.
Okay, thanks very much. We've got a couple of minutes for questions. I'm not sure I'm going to see raised hands, but try it. Okay. Any questions? I'm not the expert on this, so I can't ask you a question, really.
That is fine. If I get no questions, that's great, because it's meant to be very, very simple. Yeah. So if you have a reflectron leap, you can just let your data run through. You don't have to do anything, and the data comes out, and you can do field desorption maps nicely. Yeah, if you want to do crystallography, you can do your own reconstructions, just like if you would have a straight flight path instrument. So
yeah,
it's meant to be simple.
May I also have questions?
Yes.
Carry on.
Yeah, it's very interesting. The research work, also the calibration of the distortions. So currently, most instruments don't have this kind of calibration. Does that mean the data we collect, there are a lot of distortions? What kind of effect on the measurement results?
No, I would believe in the commercial machines, Kamika actually takes care of the corrections, but they don't hand them out. Yeah, so it's implicitly in IVAS or AP Suite, and if you do a reconstruction in IVAS or AP Suite, Kamika corrects for it. But if you would do your own, if you would take an EPOS file or ATO file, and you would do your own reconstructions or also field desorption maps. That's also something people use pretty regularly. You would have the distortions in there.
I see. Okay, thank you. It's very interesting.
You can see that very easily. If you just run aluminium, you will see that the zone lines aren't straight; they're all bent. Yeah.
Yes. We found for the instruments with reflectrons, and the disruption map is not as easy as other the straight path map to index. Yeah, the pole and the zone line are a little bit difficult. Yeah,
I think we have to move on now.
Okay.
So you could sort of stop sharing, and if the next speaker could share. The next talk is the Chase DLD system towards a fast zero dead time position sensitive detector for the atom probe tomography. And the paper is presented by Christian Backe. So please go ahead.
Can you hear me?
Yes, fine.
Yeah, and I'll try to share my screen. And here, can you see my screen?
Yes, that's fine.
Okay. So I have to apologize in advance for my voice because I have a little flu. So, hi everyone. So my name is Christian Baki. I'm a postdoc at the GPM lab, and I generally working on solutions for resolving APT spatial and compositional biases brought by the APT detection system. And today I will introduce you my last work on the improvement of the APT detection efficiency through a significant reduction of the detector dead time to 0 nanoseconds. So concretely, I will show you how I managed to recover ions that have been lost in a standard APT detection system, and precisely how this system is able to resolve the so-called multiple events, which usually involve significant compositional biases. So before going to the details of this slide, is just to illustrate the finish. I have to shortly go back to the basic principles of ion detection in APT instruments. So you have to know that after an electric or laser pulse event, a part of ions projected from the tip moves toward the first stage of the APT detector, the microchannel plate assembly, and its function is to convert ion impacts into electron clouds for generating electric signals that can be used for triggering time-of-flight measurements, followed by delay lines. Followed by delay lines, which have the function of collecting those electrons cloud on transmission lines, also called delay lines, and transferring the induced signals to each ending of those transmission lines. And so the time delays of those signals at the respective delay line ending are nearly proportional to the position of electron clouds on the lines, and then proportional to the position of ion impacts. And so finally, you can see that ion identification and positioning in APT is mainly a question of time measurement. So for accurately performing those time measurements, we conventionally use constant fraction discriminators that are able to get timestamps at a specific fraction of signal edges. And given that the approximately constant value of signal slopes, it is possible to get accurate time of flight and position measurement. The problem with this type of measurement is when more than one ion hits the detector during the same pulse event, also called multiple event. During those events, it is highly probable to get multiple impacts from the same element and from a same emission site, which can lead to signal overlaps with edges of successive signals that cannot be visible by the CFD, the constant fraction discriminator. With the CFD, so here successive signals with a delay, with a time delay under 3 nanoseconds cannot be resolved, which is called the dead time. So a solution can be found in the use of advanced delay line system, the advanced delay line system, which digitize MCP and DLD signals for decomposing overlap signals into individual signals through signal shape recognition algorithm. But when signals are highly overlapped, so precisely under 1.5 nanoseconds, the ADLD algorithm fails to recognize more than one signal. And so despite this dead time reduction with the ADLD, analysis from APT instruments using the ADLD detection system clearly showed that high losses could be stated from materials introducing high rates of multiple events. So you can see here the relative positions of secondary impacts during multiple events, where high densities of impacts are clearly stopped by a dead zone, which is the special representation of the dead time, and then suggest that selective losses may occur for elements with high multiplicities. Now to go even further, the ADLD system, we can take a look at what happens to output signals during multiple events. And here, from an analysis from the LAWA tap, one of the instruments equipped with the ADLD system, you can observe that more ions hit the detector. The more ions hit the detector, the more resulting signals are high in amplitude. So this can be explained by the fact that approximately constant value of charge quantity outcoming from the MCP is multiplied when more than one ion arrives on its open surface. So as a consequence, that information could be used for recovering ion impacts that cannot be resolved with the ADLD system. And so to go further in this approach, today I propose to the use of the charge sensitivity of delay lines, which have a higher capability to get images of outcoming charges from the MCP instead of transit signals extracted from the MCP that are more subjected to amplitude variations, as you can see on the box plot. Under this main idea, I developed a set of algorithms that I won't explain in details here, but just to say the main idea is about the charge sensitivity of DLDs that is able to determine multiplicity of an event and the best set of timestamps corresponding to the distribution of charge quantities arriving at each delay line ending. So here you have an example of electric signals from the delay line detector that I digitize, and those graphs represent what I use for my set of algorithms. For example, this one is the pixelization of the detector, and inside each square you have the median charge quantity at each position. Now, without going into detail of this, now go back to the first slide that I showed you. So here, you have to know that for comparing a standard lip detection system and the brand new Chase DLD system, charge sensitive DLD system, we work with Kamika for parallelizing the system with our digitizers for getting a direct comparison on material analysis. So those results have been obtained very recently, and I'm working hard for pushing this study to concrete development. So this one is the analysis of silicon sample. And here you can clearly see that with applying the charge sensitivity of delay lines, you have a more respectful, a higher respect of the isotopic ratios on the isotopes of silicon. And here, just to finish, I have also a comparison of the lip system with the Chase DLD system with the different heat maps, and we can see that we have clearer heat maps with the Chase DLD using the charge sensitivity of DLDs And also you can see that it works for identifying multiplicities. Done for me. Thank you for your attention.
Good, many thanks. Plenty of time for questions. So does anybody have any? Yes, Peter.
A very fundamental one. How many delay lines does your detector have?
So we use the LIP 4000HR, and on this one we have 3 delay lines, but we all for the digitizers we only use two delay lines for the moment.
Okay. So did you use information from one delay line, amplitude information from one delay line to find something out about the amplitude on another delay line?
I collect all the different charges from all endings. So from all endings, from each ending, you have a signal. You have a signal, and from each signal, I calculate the charge quantity at each ending, and after from this I can compute the multiplicity of the event, and also finding the best set of time steps for the event.
Okay, is that you finished, Peter? Okay, does anybody else want to make a comment or a question? You've obviously been very persuasive.
There's a comment in the chat, Richard. I don't know if you're monitoring this.
Oh, I haven't seen that, sorry.
Would it be feasible to do?
Okay, so would it be feasible to do curve fitting in the amplitude signal to disentangle a multiple event, for example, with 2 Gaussians? There's a question in the chat.
So the curve fitting is already done on the ADLD system, where you have, for example, 2 overlap signals that are not so close, and so we can decompose them from the envelope. But when they are too close, very so close, with an algorithm that try to decompose 2 Gaussians, it's not so feasible. That's why I use the charge quantity.
Okay, many thanks. Okay, well, I think thanks very much for a nice talk, and I think we'll move on. So could the next speaker sort of share his screen? And the next talk is a lanthanum hexaboride nanochip as an ultra-fast electron source. The paper to be given by Boradi Onkar. Go ahead when you're ready.
Just a minute, please.
Yeah, no problem. Okay, we can see that nicely.
Good morning, everyone. And sorry for my voice also. I think Christian gave it to me. So the topic of my today's presentation is using LAB6 as an ultra-fast electron emitter. I am a PhD student at GPM, University of Rouen, and I work under the direction of Professor Angela Blanc. So for starting, we have the Einstein's Planck theory, in which he explains the photoelectric effect. In 1931, Maria Gruppert-Meyer predicted the 2-photon absorption process. And then with the advent of lasers, we could see strong field effects with pulse lasers such as above threshold ionization and multiphoton ionization, in which a gas atom absorbs multiple photons to go to the excitation state. Also, similar effects were observed on nanotips prepared on based on metal nanotips at the University of Göttingen, work done by Professor Homelov and also by Professor Klaus Ropers. So here we use lanthanum hexaboride nanotip in order to understand the ultra-fast electron emission phenomena occurring with an ultra-fast laser. Why did I choose an LAB6 nanotip? Because it is a refractory metal, which makes it very strong and durable. And it also has a low work function, which says that we can have an electron emission with the coherent electrons. Also, it has a unique crystallographic structure, which makes it very conductive. It is also chemically very stable. It does not easily react to the oxygen present in the environment. And also, when you use a nanotip, the emission is confined to a very small region at the apex. So before showing you my results, I would like to take you through some of the basic mechanisms of electron emission that take place. So first we have the Fowler-Nordheim tunneling, in which you apply a very high static electric field to the sample, and which bends the potential barrier at the LAB6 and vacuum junction. So we have electron emission through tunneling. We have electron emission through tunneling. Also, we can have photo-assisted tunneling, in which the material absorbs single photon. The electrons are raised to a higher level, and then they are emitted through tunneling. With the use of strong lasers, which have higher electric field, we can see that the material can absorb multiple photons, more than one, to emit electrons from a higher energy level. So for this, we do not need a high applied static field because the band bending is lower. Also, with the high laser powers, it is observed that with solid materials, we can have above threshold emission, in which the material absorbs more than the required number of photons to emit the electrons above the energy barrier. Like as seen here, you can have 3, 4, 5, as many as possible. Also, we have optical field emission, in which the laser electric field bends the energy barrier at the LAB6 vacuum junction. Coming to my instrument, here we use a very sharp LAB6 nanotip, which is sharpened using the help of a focused ion beam. We have an ultra fast infrared laser, which is focused at the apex of the nanotip. When electrons are emitted from the nanotip, they pass through a hemispherical energy analyzer, which analyzes the energy of the electrons. The electrons are then amplified at the multi-channel plates and can be viewed on the phosphor screen. A CCD camera is used to record all the images, which gives us the ability to have 2D regional detection. So you can study different regions of the emission pattern. Also, by changing the polarity of the voltage, we can have field ion emission imaging with the same instrument. So we cool the tip down to 77 Kelvin and apply positive potential and see how the surface is, just to make sure that we have a perfect crystallographic structure at the apex and not some impurities which are emitting electrons. So till now, we have been able to achieve a single to few electron per pulse, as you can see the top left image, and also currents up to nanoampere using lasers or with the LAB6 nanotube. Also, we can see here that it gives a stable current emission with static mode, that is without the laser, and also in the laser assisted mode. Interestingly enough, when you superimpose the focal field ion emission image and field electron emission image, we can see that electron emission occurs from certain poles. So for static, you have emission only from the central 001 pole. But when we apply laser, we can see the emission occurs from the neighboring 011 family of poles. We assume that this is because the work function difference in two poles, when we apply the laser, we supply it with extra energy, which helps to activate the neighboring poles as well for electron emission. While studying the IV characteristics in the static emission regime, we can see that the LAB6 follows the Fowler-Nordheim regime, which is also proof of its metallic nature and high conductivity. If we study the IV characteristics using the laser as well, we can see that up to a certain low power of laser, we can still follow the Fowler-Nordheim regime. If we decrease the voltage and increase the laser power, now we can see that the emission mechanism is a little bit different. Now from Fowler-Nordheim regime, we shift to something which is almost voltage independent. So now the emission is occurring mostly through multi-photon emission. So the material is absorbing multiple photons and the electrons are emitted above the energy barrier. And if we go on decreasing the voltage, so now we remove any probability of having tunneling emission. We can see that with a higher laser power, the Fowler-Nordheim in Fowler-Nordheim coordinates, the plot is inverse of what it should be for a metal. This is also because of now we are shifting into the strong field emission regimes. We see above threshold emission and rescattering and other such effects taking place at the tip apex. If we study the electron energy spectra, we can see here that for static emission, that is for when the laser power is 0, we have a single peak here around the Fermi energy level, which is lower than 1 eV. If we apply laser and keep on increasing the power, we see that a peak appears around 2 eV, which goes on increasing with the increasing laser power. This is because a multi-photon absorption process is taking place here, which absorbs up to 3 or 4 photons to emit the electrons. Also, the advantage of the 2D detector gives us if we study these different regions, we can see that clearly for the central spot, we have something which gives us a peak near the Fermi level. And for the remaining spots which are on the side, we have only one peak, which is on the multi-photon, which we call the multi-photon emission peak around 2 eV. If we study the emission spectra at lower applied voltages, that is, we remove the probability of tunneling emission, we can see now the electron energy peak is now shifting towards higher values, which means that the material is absorbing more and more photons to emit all the electrons. And if we continuously keep on increasing the power, we go into the strong field emission regime. And here we see what we call could be probably higher harmonic generation at the tip, in which we have electrons up to 10 eV. In some cases, we have even observed up to 30 eV. So we have electrons with much higher energy than the work function of the material. To summarize my results, we have achieve stable electron emission, and also the ability to emit single electron pulse, which can be very useful for diffraction experiments, and also high currents, high beam currents to have good contrast imaging. We could control the electron energy of the emitted electrons using applied static field and also with the laser electric field. And it is highly possible to use such electron sources in modern ultra-fast X-ray optics and also ultra-fast electron microscopy and other ultra-fast experiments. So that's all for me. Thank you for listening.
Okay, thanks for a very nice talk. Anybody have any questions? Nikita.
Sorry, it's a question from last time.
Ah, okay. Anybody else? Okay, I have a couple of questions.
Yes.
What are the merits of lanthanum hexavoid as compared with tungsten, which is sometimes used for these sources?
So tungsten has a higher work function, which inherently makes the electron emission less coherent than what we have for LAB6. And also what we have observed is that using tungsten, it's not much stable. Like within 8 or 9 hours, we lose 80% of the emission stability. But here we have used it for 9-10 hours without losing any stability at all.
Okay, that's and could you go back earlier? There was a slide earlier which I didn't quite catch with the Fowler-Nordheim equation on, or a version of the Fowler-Nordheim equation.
This one?
No, the one before, I think. Yeah, you do need to be careful. What's the interpretation of your capital B in there? Your capital B.
Capital B is a constant.
Yeah, okay, that's what I thought. Now, that's the equation that was developed in 1929, essentially.
Yes.
But it was shown in the 1950s that Fowler and Nordheim actually got the theory wrong. And the more correct equation is the Murphy-Good equation. The field emission, which has got a correction factor there, and it predicts currents about 500 times higher. But the Fowler-Nordheim paper is extremely misleading. If you actually check it against the experiment, the discrepancy with the experiment is about 10 to the power 15 in the 1928 paper. And what is misleading about the literature is that the Murphy-Good equation is often called the Fowler-Nordheim equation. So if you look in the field emission literature and it says Fowler-Nordheim equation, it's nearly always referring to the equation developed by Murphy and Good, which predicts much higher currents. And this is a mistake that's extremely wide. So that's just as, it doesn't matter, but it's better to write down an equation that predicts 500 times as much current.
Okay, yeah, thank you for the point.
Okay, I think we need to move on now. Thanks again for the talk. If you could stop screen sharing, and if the next speaker could share the screen. The next talk is a photoluminescence study of field evaporation mechanisms by Eric Wykeham.
Hello, everybody. Can you hear me?
I can hear you, but can't see your screen yet.
Okay. Wait, here we go. Now we can see it. Right?
Yes, but you need to expand it.
Yes, of course.
Okay.
Can you see the slides?
Yes, that's fine. Everything's fine.
Okay, perfect. All right. Hello, everybody. And thank you for the opportunity for me to present my results here at the conference. My name is Eric Wykeham, and I am a PhD student at the group of material physics. at the University of Rouen. My supervisors are Angela Vella and Lorenzo Rigutti, and I would like to share with you my research on our photonic atom probe setup, which I will get to now. So the photonic atom probe. First of all, at atom probe tomography, at laser-assisted atom probe tomography, we use a femtosecond laser in order to excite our specimen. Now, if after the excitation of our specimen by a femtosecond laser, we always obtain a photoluminescence response from our specimen itself. And with the photonic atom probe, we use a hemispherical mirror in order to catch our photoluminescence response and to perform photoluminescence spectroscopy on this called photoluminescence response. The specimen that I'm discussing here is a zinc oxide, magnesium zinc oxide double quantum well system, where the two quantum wells are at a distance of 60 nanometers, thus they are not coupled. So fundamentally, what we get from the experiment is we get a constant recording of photoluminescence spectra while our specimen is evaporating at the same time. And so we are able to correlate the shape of the specimen with its photoluminescence signal, and we are also able to perform high fields optical studies on matter. Now, a question that I've asked myself is how does the geometric evolution of the specimen influence the photoluminescence behavior? And in order to study this question, I have used our photoluminescence emitting quantum well number 1 as a localized probe in order to study the emission behavior of our specimen during field evaporation. Now, one thing that we have observed is our peak shifts in the photoluminescent signal during the specimen's field evaporation. These shifts in the photoluminescence energy can be mostly traced back to voltage-induced mechanical stress effects, which has already been published here. Now, my work, on the other hand, mostly deals with the question of the development of the quantum well photoluminescence intensity during the TIPS field evaporation. And firstly, what we observe is that for early evaporation stages, we see a rise in quantum well photoluminescence intensity, which means that if we remove atoms that are far away from our photoemitter, we for some reason measure an increase in its photoluminescence intensity. And then, of course, after we have reached the peak and once at the latest points, once the quantum well itself starts evaporating, we see how the photoluminescence intensity starts going against zero. In order to simulate the photoluminescence behavior, I have performed finite difference time domain simulations using the numerical framework. And firstly, I have simulated the absorption of the pulsing laser at the region of the quantum well in order to get an idea about the strength of the quantum well emission. And secondly, I have studied the distribution of the emitted light, which is being emitted from the interesting quantum well, in order to calculate the detection efficiency by calculating the fraction of light which is being caught inside of our field of view. These two simulations I have performed for a set of different TIPS geometries, which are evolving dynamically as a function of the depth of analysis. So basically, for each of these geometries that I'm showing you right now, I've performed both absorption and emission simulations as a function between of the distance between the evaporation front and the quantum well itself. And the emission simulation themselves were performed on three dipole orientation, which are along the cardinal axis of our system, which are the x-axis, which is the axis of the atom probe setup, the z-axis, which is our optical axis, and the y-axis, which is perpendicular to both of these. So basically what we end up with is we get a measure of the relative amount of light which is absorbed as a function of the distance between our current position of the evaporation front and our quantum well, and we obtain our detection efficiency or geometrical yield as a function of the same distance. Combining these two results allows us to obtain the absorption weighted yield, which can be used as a measure to see if a combination of our emission and absorption simulations is able to explain our experimentally observed behavior. And so here I show you the results for all three dipole orientations. And as we can see, the Y-oriented dipole shows a qualitative agreement with the experimental data in that it shows an increase for the early evaporation stages. The other simulated dipoles do not show this early increase. So the best agreement we get is using the Y dipole. And in our previously published work, we have already shown that indeed, this is the expected dipole orientation for emission with our measurement configuration. Now, what we cannot explain is why the photoluminescence intensity already starts dropping before the quantum well itself starts evaporating. And something that I have not taken into consideration yet is that, of course, the properties of our material and high electric fields will drastically vary. Firstly, at a high electric field, we see a shrinkage of the band gap. Secondly, we see an accumulation of surface holes close to the tip's apex. And thirdly, we can also expect additional resonances in our system, which come from the fact that we have holes bound to our surface by the high electric fields. So what we can expect is a drastic increase in the absorption coefficients. And so what I have done is I have defined in our simulation space a volume, which is supposed to be highly absorbing. And indeed, as a first estimation, I have introduced a perfectly absorbing layer. Now, if we think about the effects that a high absorption coefficient has on the refractive index, we get to the point that basically a perfectly absorbing layer also is a perfectly reflecting layer. And so basically, in order to model strong light matter interactions, I have assumed that all the light that comes in contact with this top layer is completely reflected. If we perform the simulations containing these perfectly reflective top layers, we will see a change of the behavior. Firstly, the absorption will show a significant drop before the quantum well number one itself starts evaporating. And secondly, the previously described local maximum of the photoluminescence intensity given by the Y dipole orientation is way better described here. So here now we are able to describe the fact that we have the strange local maximum in the measured photoluminescence intensity for the Y-oriented dipole. And so basically this perfectly reflective layer gives a decent explanation for the experimentally obtained behavior. Now, for our conclusions, we can see that a highly reflective layer indeed gives us the best theoretical representation of our experimental results. And so the basic point to take away from these results is that this is another hint that the optical and thus also the electronical properties of the top layer in the atom probe tomography drastically differ from the bulk behavior. And one thing to keep in mind with this whole story that I'm telling you is that my simulations are only considering the amount of light absorbed by the specimen and the change of the setup yield as a function of the specimen shape. What I did not take into consideration are any effects of the transport properties of our charge carriers, which are where the transport indeed can be expected to play a major role due to the high residual fields inside close to the atom probe tip's apex. And for the future, we are looking forward to study more complex structures like this tunnel junction, for instance, using the photonic atom probe. And secondly, we are looking forward to study the behavior of coupled quantum well systems in order to study the transport behavior of charge carriers by their photoluminescence response. So thank you very much for your attention, and I hope there's time for a question.
Yes, plenty of time for a question.
Perfect.
Okay, does anybody have any questions? Okay. So, where is all this going? Would be my question.
Fundamentally, I would like to, like I said, fundamentally, the quantum well itself, which is embedded in our specimen, I would like to use it as a localized probe to study the behavior of the photonic atom probe setup, in order to give us some background to study a highly complex signal, which we would expect from a more complex specimen, in order to basically, this is a minimalized model for what we can study with the setup, if we understand this minimalized model properly.
Looks to me like you've got a very complicated problem there.
Yes, already this minimalized problem, I bet you saw it. I took some major simplifications.
Okay.
And yeah.
Has anybody else sort of thought, has a question occurred to anybody else whilst we've been talking? Okay, well, thanks for a very nice and intriguing talk.
Thank you very much for the opportunity, Mr. Forbes.
Yes. Okay, so we will now move on to the next speaker. If you could remove your screen, I will have to adjust it. So I've managed to lose the. Okay.
Can you see my screen? Can you hear me?
Yes. Okay. And as you can see, the next talk is comprehensive investigation on restarting AFM measured APT emitters by that set of authors. The talk to be given by Yuan Chu, I assume.
Okay. Can you hear me?
Yes, everything's fine, except you need to probably sort of go into a full screen mode. We can still see the left.
Thanks for your introduction.
Yes.
I'm Yuan Tu from IMEC. Today I'm going to share our progress on comprehensive investigation on restarting AFM measured APT emitters. Atom probe is a powerful technique for obtaining three-dimensional elemental distribution maps, but when it is applied to analyze semiconductor devices like gate-all-around transistors or FinFETs, it always gives a distorted image. The reality is, the emitter geometry is always not hemispherical, so it is supposed to be during the reconstruction. The emitter geometry determines the field, and that determines the ion trajectories, and that can be the origin of artifacts. Normally, we use SEM or TEM to check the geometry of the emitter geometry, but they always provide a two-dimensional image with not so good resolution. Electron tomography may provide 3D information, but it is just time consuming. AFM, or atomic force microscope, is a standard tool for topography measurement. It uses a cantilever with a very sharp probe to scan the sample surface to get the up and downs of the surface. In our previous work, we demonstrated that we achieved the alignment between AFM probe and the APT tip. So we can perform an AFM measurement on the APT tip. And here's the result. It is normally shown in 2-dimensional, but we can also show it in 3-dimensional. Okay, so AFM can provide a 3D image of the geometry with rather high resolution. So what can we do with it? We hope to improve the atom probe data reconstruction. The concept is the region between 2 AFM scans can be reconstructed based on the geometry measured by AFM. And here's one example. We have a sandwich structure with oxide protruding, with oxide in the middle, and it's protruding on the top. Here is AFM result. If we perform a normal reconstruction based on the assumption that the surface is hemispherical, the thickness of oxide will always be overestimated. And if we perform a reconstruction based on the tip shape we measured by AFM, the thickness is more reasonable. But about this concept, there are still several concerns. How about the yield or successful rate of restarting AFM measured tips? So it is about that after AFM measurement, can you really put it back to atom probe and restart it again? And the second question, does AFM bring contamination? The third one, can we restart real tips? Can we show some typical application cases? So this is what I'm going to address in today's talk. And here is the experiment design for investigating the role of AFM on yield and surface contamination. And we have atom probe in one building and AFM in another building, and between them is 10 minutes walk on the street. We choose a standard PSM as our sample, and we put it in atom probe for the first measurement, and then we take it out for AFM measurement, and then we put it back for the second atom probe measurement. So for each tip, we will have 2 data sets like this. And here's the process. We stop the measurement and we take it out so it's exposed in the air, and we go to AFM and we put it back to perform the realignment between tip and electrode, and then we restart. But to evaluate the AFM measurement itself, we need to eliminate the interference of other steps. So we have another 3 groups. Group 1 that we stop and immediately restart. Group 2, we stop and we home the stage and perform a realignment before we start. Group 3, we take the sample out and put it in the laboratory, and then we put it back. And group 4 is only group measured by AFM. So you don't have to remember all of this. Just remember that group 1 and group 2 are preserved in the lensed chamber of atom probe, so it's in ultra high vacuum. And group 3 is exposed in the air. Group 4 is exposed in the air and measured by AFM. And here is the result about yield. As expected, all the tips in group 1 to 3 are restarted successfully. And for group 4, we take the sample out and measure by AFM. And here is the AFM result of the 6 tips in group 4. And when we put it back to atom probe and restart it, it turns out all the 6 tips are restarted successfully. Okay, so that indicates a 100% yield for restarting AFM measured tips. And here I show the atom maps of group 1, 2, 3, 4. That 1 and 2 are in ultra high vacuum, so the top is quite clean. And group 3 is exposed in the air, so we see some oxygen. And group 4 is measured by AFM, so it seems we see more oxygen and carbon contaminants. And here is a voltage curve of group 4. We have the first measurement, and then we take out for AFM and we put it back. And the voltage increase to remove this surface oxide or contaminants. And then it drops to a reasonable value to measure the silicon PSM. And we achieved this 100% yield with the slow start method. At the beginning, the surface is totally covered with oxide. We set the detection rate 0.02. And when silicon is exposed and start to evaporate, we change the rate to 0.2. And when oxide is totally removed, we change the rate to 1%. That is same with the first measurement. Here I show the mass spectra of these 4 groups. Group 1 and 2 are in high vacuum, so the mass spectrum is quite clean and they're almost identical. In group 3, it's exposed in the air, so we see more oxygen and we observe carbon peaks. And for group 4, it seems we observe more oxygen and more carbon and more hydrogen. But except for these 3 elements, we didn't see other strange peaks like metal or something else. So this was the most the dominant contaminant elements. Then we noticed that it's unfair to compare group 3 and group 4 like that, because group 3 is always in this laboratory and it's never taken out of it. It didn't experience the transfer. It was not put into the other laboratory and it was not put into the chamber. So we considered another 4 groups here, we consider different transfer methods: transfer in the air, transfer with a nitrogen box, and we put it in the chamber, or put it in the chamber and pump it to vacuum, or just put it in the room. Okay. So we have another 4 groups, A, B, C, D, and only group D is measured by AFM. For group A to C, no matter how do you transfer when you walk in the street, but before you put it in AFM or after you take it out from atom probe, the samples are still exposed in air. So group A to C is the samples are all in air. And here's the result of these 4 groups. And we observed this contamination or oxidation for all of these 4 groups. Okay. And if we generate a new region of interest, we can calculate the areal densities of hydrogen, oxygen, and carbon. Only group 4 is measured by AFM, and we didn't see a clear increase of these contaminant elements compared to the rest 3 groups. That indicates this contamination is introduced during this XC2 transfer rather than AFM measurement itself. And finally, let me show some real application cases. The first one is silicon solar cell, and the structure is like this. We successfully performed the cycling measurement. We have the first atom probe measurement, and it goes through silicon cap, and we stop it in polysilicon. And then we take it out for AFM measurement, and we put it back for the second atom probe measurement. Here we intentionally stop at the interface between polysilicon and substrate with the oxide in the middle. And then we take it out for AFM measurement, and we can put it back for the third atom probe measurement. If we want, I think we can still try to extend this, this cycling measurement. And before we start AFM2, the measurement goes to the interface between polysilicon and substrate. And this is the pattern on the detector. So we think that the inner part, this is polysilicon, and the outside part is silicon substrate. And the ring shape is oxide. And we can also see the distribution of oxygen here. And this lower density of this ring shape indicates the oxide might be protruding on the surface. And we observed this by AFM. And indeed, we observed this ring shape. Okay, so AFM is able to show this fine topography when it measures to the interface of a much layer structure. And the last sample is nickel aluminum polycrystalline thin film. It is supposed to be the next generation interconnect material to replace copper. If you noticed my colleague Jeroen's talk yesterday, he observed some density variations in the result, which is maybe is correlated to the microstructure and the emitter. So we perform the AFM measurement. It looks like this. And if we perform a scan in the topmost region, we can have a topography image. Here I show this image with a ratio that Z coordinate is doubled to make it more obvious. We can see some morphologies. with this topography data, we performed a curvature analysis. So we get a curvature map. Okay, until now, that's interesting. But when I try to mark the region with lower curvatures with red dots and connect them with wires, we can see a pattern. Okay, let's see it again. I mark the regions with lower curvature with red dots and connect them with wires, we can see a pattern. This pattern is in good agreement with the pattern on the detector. Okay, so if you don't trust your eyes, we use some algorithms to calculate the correlation coefficient between these two images. And it turns out this coefficient is much higher for these two images compared to the correlation between this image and the curvature of a PSM. Okay, so lower curvature on the emitter is corresponding to the higher density on the detector. This is what we observed by AFM, and it shows the advantage of AFM against other techniques for this application. In summary, we investigated the influence of AFM on APT tips. All the PSMs measured by AFM can be restarted, and the oxidation is likely due to air exposure during the transfer, and no evidence shows AFM bring additional contamination. And second, we show some real application cases with real samples. The cycling measurement is successful, and AFM resolves the tip shape at the interface. We see the ring shape in silicon solar cell, and we demonstrate this ultrafine curvature variations that is linked to the density variation or microstructure in the nickel aluminum sample. Above all, AFM method is very promising to improve APT data reconstruction. In particular, if we consider a vacuum transfer system or even in situ system. Thanks a lot for your attention, and welcome to Nerven for the next APT&M conference. Thank you.
Okay, thanks again for a very nice talk. Any questions?
Yes, briefly. Great talk. How did you manage to get your AFM to get down to the tip and contact without causing, without hitting it and causing damage? Because that's a very challenging thing to do in air.
Yeah, so as we can see that these two tips are very sharp, perhaps the sharpest tips on Earth. And if we apply a voltage between them, they will generate electric field. And this electric field will have an electrostatic force between these two tips. And we operate this tip with taping mode, where the probe is vibrating, and the electrostatic force between them will lead to a phase shift of this of vibration of this probe. And by detecting the phase shift, we can perform a scan to detect phase shift, and we can gradually shrink the scan area and down the stage a little bit, and continue to do that. And then finally, we will make the tip very close to our atom probe sample. And then if we perform the engagement, the probe will be landed to somewhere near the center, but you can gradually move it to the center.
Okay, thank you. I was wondering how you were sensing that.
Yeah. You can also check our previous papers. We have a detailed introduction about that.
Anybody else have any questions or comments? Okay, so thanks very much. Nice. Sorry.
Oh, sorry. Can I ask a question? It's like, for the AFM, is also suitable for testing the surface structure of softer matter tips? Thank you.
It depends on how soft it is. Currently, we use taping mode, so it is also called non-contact mode. So in ideal situation, the probe is not really contacting, it's not really have a mechanical force on the sample. But until now, I don't have experience of measuring a soft matter tip.
Okay, thank you. It was nice talk.
Yeah, thank you.
Okay, is there a question in the comment, or happy to just have that answered? Does the tip shape have consequences for the reconstruction?
This work is really a recent work. We observed this data perhaps 2 weeks ago, and we are still trying to investigate more on this. But at the current stage, maybe we didn't see how this contributes to the reconstruction. But in the future work, we will try to do that.
Okay, so thanks very much again.
Thank you.
And this brings the session to an end, I think. So thanks to all the speakers for keeping to time, I think we should say. And we come back again in 15 minutes.
Nanjing, the capital of Jiangsu province, is an ancient capital of the 6 dynasties with profound historical and cultural heritage, and a modern international metropolis that is friendly, livable, tolerant, and open. Nanjing University of Science and Technology, established in 1953, is located in the most beautiful Zhongshan scenic area of Nanjing. It is a national key university affiliated to the Ministry of Industry and Information Technology. Upholding the motto, dedication to truth and innovation, NJUST actively integrates into the country's manufacturing and network construction, the Yangtze River Delta region development, and other major national strategies and regional economic and social development. With the strategy of 1 university and 3 campuses, NJUST has been committed to multidisciplinary development on engineering, science, medicine, human sciences, management, economics, and law. As a key university of 211 project, a member of 985 innovation platform, and a double first-class construction universities and disciplines, NJUST has been dedicated to mounting up to the plateau and peak of superior diversified disciplines. The university has 4 disciplines ranking in the top 1% of ESI disciplines, with engineering is in the top 1,000th globally. The university has 15 academic colleges, more than 2,000 full-time faculty members, 20 academicians, around 30,000 students, including 1,000 international students. Innovation is the key to the university's academic excellence. NJUST has more than 50 research platforms at the provincial and ministerial levels or above, and has undertaken a large number of major national scientific research tasks. NJUST has made fruitful innovation achievements on the way of continuous improvement in basic research capabilities and deepened coordination of industry, academia, and research. It has become an important base for scientific and technological innovation in China. NJUST has won 105 national scientific and technological awards, including 9 national first-class awards. As an academician of CAE, Professor Wang Zishan won the 2017 National Super Rim Award for Science and Technology. NJUST has been optimizing talent cultivation mode. The university devotes itself to cultivating innovative and elite talents with international competitiveness to lead the future. More than 230,000 NJUST alumni have graduated and been serving as innovative academic leaders, industrial elites, and pillars of governance for the country. NJUST students have won many awards in major events such as the Internet Plus Student Innovation and Entrepreneurship Competition, the Challenge Cup National Extracurricular Academic Science and Technology Competition, the Postgraduate Innovation and Practice Competition, ICANN International Contest of Innovation and International Collegiate Programming Contest. NJUST vigorously promotes the process of internationalization and has established close cooperation with more than 200 famous universities and research institutions abroad. With joint efforts, NJUST has established international cooperative bases such as Herbert Glader Institute of Nanoscience with KIT, Sino-French Engineer Institute with the University of Lorraine, Technology Innovation Support Center with the World Intellectual Property Organization, to carry out cultural exchanges and promote mutual understanding among civilizations. The university has set up research centers on the Kingdom of Saudi Arabia, the Republic of Belarus, Central and Eastern Europe. Stepping into NJUST campus, there is strong academic atmosphere where elites and masters work side by side. Here stand the verdant and upright forest, the elegant Zixia Lake. Students embrace the vibrant campus life. Here, the pulse of Chinese history and culture can be touched. Students experience the speed of development of modern China. On the pursuit of truth and innovation, steps never stop. Explore the world of new knowledge and meet the bright future at NJUST. Nanjing, the capital of Jiangsu province, is an ancient capital of the 6 dynasties with profound historical and cultural heritage, and a modern international metropolis that is friendly, livable, tolerant, and open. Nanjing University of Science and Technology, established in 1953, is located in the most beautiful Zhongshan scenic area of Nanjing. It is a national key university affiliated to the Ministry of Industry and Information Technology. Upholding the motto, dedication to truth and innovation, NJUST actively integrates into the country's manufacturing and network construction, the Yangtze River Delta region development, and other major national strategies and regional economic and social development. With the strategy of 1 university and 3 campuses, NJUST has been committed to multidisciplinary development on engineering, science, medicine, human sciences, management, economics, and law. As a key university of 211 Project, a member of 985 Innovation Platform, and a double first-class construction universities and disciplines, NJUST has been dedicated to mounting up to the plateau and peak of superior diversified disciplines. The university has 4 disciplines ranking in the top 1% of ESI disciplines, with engineering is in the top 1,000th globally. The university has 15 academic colleges, more than 2,000 full-time faculty members, 20 academicians, around 30,000 students, including 1,000 international students. Innovation is the key to the university's academic excellence. NJUST has more than 50 research platforms at the provincial and ministerial levels or above, and has undertaken a large number of major national scientific research tasks. NJUST has made fruitful innovation achievements on the way of continuous improvement in basic research capabilities and deepened coordination of industry, academia, and research. It has become an important base for scientific and technological innovation in China. NJUST has won 105 national scientific and technological awards, including 9 national first-class awards. As an academician of CAE, Professor Wang Zishan won the 2017 National Super Rim Award for Science and Technology. NJUST has been optimizing talent cultivation mode. The university devotes itself to cultivating innovative and elite talents with international competitiveness to lead the future. More than 230,000 NJUST alumni have graduated and been serving as innovative academic leaders, industrial elites, and pillars of governance for the country. NJUST students have won many awards in major events such as the Internet Plus Student Innovation and Entrepreneurship Competition, the Challenge Cup National Extracurricular Academic Science and Technology Competition, the Postgraduate Innovation and Practice Competition, ICANN International Contest of Innovation and International Collegiate Program.
Well, welcome back. Welcome to the last session for this conference, the 14th technical session. Just while I'm here, I'd like to say congratulations and thanks to Gang and his team for putting on such a great event to bring us all together. And my name is Ross Marceau. I'm from the University, from Deakin University. I have the pleasure of chairing this last session on geological and biological material and reconstruction method and data treatment. So our first speaker is Richard Forbes from the University of Surrey, continuing on from chairing the last session. Richard, I can see you've got your slides ready, and we're pretty much there on time. So if you want to get cracking, please go right ahead.
Right. Renewed steps towards a better basic science of field evaporation. We gave this up in about 1995, and we better start again, is my point. It's about the basic theory of field evaporation. Now we've got modern density functional theory in place, and it seems to be working well. I think it's time to look again at how to establish a satisfactory basic science of field evaporation. Best starting place is metal elements, although what we're really interested in is much more complicated. And I take a top level look at some of the issues involved. So that's the topics. I'm going to spend most of the time on the first one, because if we're going to have a standards session next year, then many of the details of the others are better placed there. But I have a few comments and other things. Right. The fundamental atomic level constant N1 denotes the amount of substance of a system that contains one specified entity. This is something I have been arguing for. Normally, the nature of the entity needs to be specified, for example, an atom at high risk of evaporation. Once you've defined the constant, you can define a unit by that equation. I'm calling the unit the entity for convenience. Eventually, I think we might have a better name for it. And the unit, the entity, can then be used to define other units of amount of substance. In particular, the mole is equal to Ra entities, where that is the Avogadro number, which now, since May 2019, has an exact value. But you can also use it to define other units of amount of substance, or counting units, a dozen, a gross, a six-pack, and so on. All these units are counting units. And a counting unit is not a pure number. If you consider the sentence, in the line to buy tickets, I was in position dozen, it is simply not correct English. You can't put a counting unit in a sentence like that. And that shows that even in English, a counting unit is not the same thing as a pure number. Any pure number in English can be turned into a counting unit by adding pack. And use of a counting unit normally implies that the object being counted needs to be specified. Now, in science, the object being counted are scientific entities, like as per the usual standard. There's nothing to stop you defining the entity to be a medium-sized egg or a specified can of beer. The process of counting applies perfectly well in science and in normal life. It's just the committees don't recognize this yet. Okay, in science, counting units are described as being units of amount of substance. This has its own formal dimension denoted by that type of N. Obviously, the mole is recognized by the International Standards Organization and the other units are not, but they could be made recognized by the definitions above if one wanted to. Now, for atom probe, a major problem is that the International Standards Organization is a bit foot-draggy. And it doesn't accept yet that the mole, as defined, is a very large counting unit. And it dislikes references to counts and counting in international standards. And of course, we've been counting atoms for 60 years, and they still won't recognize it as a scientific process. Now, amount of substance is not a helpful name for quantity that's actually a count of specified entities. But if we tried to use any other name, it will cause fusion. So when I say amount, think count. Now, then we have to do another bit of linguistics. A physical property is a property of the physical world, and that exists independent of how we choose to describe it. A physical quantity is a man-made mathematical entity used to quantify it. The ideal situation is to have one quantity per property. Sometimes there are alternative choices, sometimes changes are made. So in the 1970s, electric fields changed over from being Gaussian fields to modern fields, which are actually called ISQ fields, International System of Quantities fields. But an ongoing situation of this kind occurs with the basic equation of field evaporation. If we formulate in terms of properties, how many atoms per unit time are field evaporated, that is the product of how many atoms are at high risk, king site atoms in practice, and the field evaporation rate constant for the king site atoms. If you do a more detailed treatment, you can put it into this form. So then there are two formulations. There's a 7-dimensional one using amount of substance. Look at the left-hand box. That's the amount or count of atoms per unit time. The symbol I prefer to use is phi7d. It's measured in atoms per second, and its dimensions are nt to the -1. And that is the product of two other things. If you look at the middle box, it's the amount of atoms. Atoms is treated as a unit of amount of substance. Alternatively, you can use the 6D formulation, in which case what I call the 6D flux is measured in seconds, and you deal with the number of atoms, which is dimensionless, rather than the count of atoms, which has dimensions. And there's the little relationship at the bottom between the two types of N. Now, these equations reflect a wider problem. ISO decided in the 1970s that calculations relating to large amounts of substance should use 7D equations, but calculations relating to small amounts of substance should use 6D equations. It didn't really decide that. They just changed it from number of gram molecules to moles. This decision has caused and is causing enormous confusion if you look at Wikipedia. And the best long-term solution is to use 7D equations for everything, but particularly an atom probe, in my view. I wrote a paper on that a little while ago. Now let's go back to this. The key question is, if you look at the left-hand side, what do you want to measure how many atoms evaporated per unit time in? Do you want it to be atoms per second or reciprocal seconds? If the first, use a 7D system. If the second is a 6-dimensional system. Now, my perception is we've got to decide which of these equations we use. And the essential question is, what do you want? Is it going to be seconds, entities per second, or atoms per second? Now, I think the most common practice is atoms per second or ions per second. And that speaks for the use of a 7D formulation. Now, another thing that the committees won't like is use of the word atom, because they say it's not a unit of amount of substance. Well, that's easy. You just have a special rule. In circumstances where no confusion can arise, the unit name, the entity, or whatever they choose, can be replaced by the name of the entity being counted. In fact, the chemists do that anyhow, and you see per molecule or per electron in the literature quite often. So that's that. Now let's go on to fields, what you have to do with fields. I'm trying to say what needs to be done. You need to distinguish the different types of electric field, in particular electrostatic and electromagnetic. They behave in physically different ways. And obviously, simple field evaporation theory is mainly concerned with electrostatics. Then you have to decide which field-like quantity is being measured. If it's post-field ionization, the field's outside the critical surface. If it's field evaporation, it's something closer to the surface. If you're actually calibrating with reference to field electron emission experiments, actually it's the field that determines field electron emission. So that there's a lot of thinking about precisely what's being measured. Then there are conditions under which it's being measured. Is it the zero barrier field? Is it the operating field in a pulse situation? Is it the onset field in DC field evaporation? So you have to specify again the conditions under which it's being measured, and we are not very good at that. Ambiguities over the meaning of the term evaporation field should be removed, and I think that's a task for next year, or to start on it anyhow. Then there's the problem of measuring fields. There are several different methods, none of which is accurate, essentially because to do a measurement, you've got to have a reliable theory involving field. And none of the processes you might use have got reliable theory as of now. So best practice is try to formulate the theory in terms of a ratio of fields, so that problem goes away. Can't do it for everything, you can do it for useful things. Okay, now the next point is that obviously field evaporation is traditionally explained as a thermally activated process over what I call a charge draining hump. The thing's partially charged on the surface, comes off the surface, partially charged, and ends up as integrally charged by a method that we simply do not know. And there is massive evidence that this is the case. And in particular, it's usually assumed that the laser pulse atom probe works by pulse heating. But some recent publications have suggested instead that field evaporation is a bond breaking process induced by maximal stress. This is a different story. The publications involved have generated interesting results, but my opinion is they do not overturn the traditional basic explanations. Well, this issue needs more detailed examination, and I can't do it here. Right, what we actually want as the key to field evaporation theory is an expression for the activation energy as a function of field. At present, in classical theory, 3 different expressions are used for different ranges. A low Q, which is pulse atom probe conditions, Q is taken to be nearly linear in F. It may not be exactly linear. Slightly higher Q, which is continuous field evaporation conditions, as in old VLR microscopes. You derive Q by assuming ion core vibration in a parabolic potential energy well, which gives a certain formula, which is not quite the same as 1. And at high Q and high temperature, you assume it's in a Lennard-Jones well, and Kreutzer a long time ago derived a formula for that. So what we need doing with the modern DFT theory is derive a good quantum mechanical expression for Q of S and see if these three regimes can be identified. And if not, try to find out what the cause of the problem is. So question, what material do we use? Well, calculations for metals have been calculated by aluminium by Sanchez and for tungsten by Christoph and his group. And we heard in a poster other calculations. Now, neither aluminium nor tungsten is good. It's been known since the 1970s that aluminium has slightly anomalous behavior, and so it's not very good to use. Tungsten appears to evaporate directly as 2+, so that's not very good. My understanding is that really for tungsten, you should use relativistic quantum mechanics, so that's not helpful. The best material is clearly rhodium, and it's a good material because there are very careful measurements. Ernst got a national prize in Germany for the measurements on rhodium and got the theory right before Kingham did, incidentally. And so you can compare experiments, classical theory, and quantum mechanical DFT theory for rhodium with more ease than for any other material. Now, it's firmly established that rhodium evaporates as 1+ and then post-ionizes. That's an experimental result. By contrast, classical field evaporation theory predicts direct ionization as 2+. So there's an opportunity to demonstrate superior performance of DFT theory in predicting this, providing you formulate the DFT theory so you can work out the charge around the evaporating ion core. The other thing is that all the Kingham curves are obtained by calibration to the Ernst results, which at that time, and still probably are incompatible with the classical field evaporation theory. So if we look at rhodium, there could be a later opportunity to explore the validity of what Kingham did. But actually, there are quite a lot of errors in the Kingham mathematical treatment, so you have to take those out before you can back down to the basic physics. So that's my brief account of what needs doing. Obviously, a lot of further issues like the reaction path. Does it go straight off? Does it go sideways? Does it sort of go sideways into a bonding state and then go off somewhere, as we heard from a poster? Then there are multi-ion evaporation vents rather than funny things that happen in the vacuum space. Then there's the question of atom probe optics and image compression factors needs looking at again, in my view. And then you want to try and do these things with metal alloys and non-metals in several years' time, to put it mildly. So thanks for your attention.
Great, thank you very much, Richard. Much to do.
Yes.
Does anyone have any questions for Richard? Christoph.
I was just clapping for the timing. I had one question. No, but I will ask this later directly to Richard because it's a more lengthy question.
We need to do a lot of talking.
Yeah.
Does anyone else have a question they'd like to ask Richard? Well, yeah, feel free to utilize the chat box. That's been working well. So I'd like to invite our next speaker, Sham, from MPIE in Düsseldorf, Germany. Richard, if you could stop sharing.
Yes, I was just looking for how I do it. I tend to sort of lose the relevant box.
Can you see my screen already, or?
Not yet. Got to get Richard to stop sharing. It's.
I don't do this very often. Oh,
there you go. All good.
Yep.
Shams, yours is there, but you need to put it into a different presentation mode.
Okay.
So Sean's going to talk to us about, well, it's a question here, are vacancies in field ion microscopy artifacts or not? a D of T study. Thank you.
Yeah. So now you see my screen in presentation mode.
Yep, all good.
Thanks Ross for the introduction. I'm Shyam. I work in Department of Computational Materials Design, working with Christophe and Baptiste and Max Planck Institute for Horizon Fusion. And today I would like to answer this question: are vacancies in field line microscopy artifacts? Basically try to do this with a density functional theory study. So before I try to answer the question, let me just briefly introduce what is actually field line microscopy for some of the younger colleagues. So FIM is a predecessor technique to atom probe tomography, and it is actually one of the first techniques to image individual atoms on the surface of a metal specimen. So the way it works is that you basically take your sample and make it into a very sharp needle with typical end radius less than 100 nanometers, which is same as in atom probe tomography. And then you apply a bias and introduce an imaging gas, usually an inert gas. And the consequence of the specimen shape being a sharp needle is that you create a humongous field at the apex of the specimen. And this field is typically 10 power 10 volts per meter. And such high electric fields basically causes the ionization of these introduced gas atoms. And these gas ions then basically are repelled away from the surface of the specimen towards the phosphor screen, wherein it creates an image on the phosphor screen typically. Now, another interesting effect of basically using crystalline materials and making them into sharp needles is that you end up with terraces, which have steps, kinks, and all these sorts of things, right? And it has a consequence that when we apply bias onto our specimen, the charge distributed on the sample is not random or homogeneous, but it has a certain pattern. That is, as you can see, that usually the charge is more towards the edge of the specimen than in the middle of the terrace, which means that if you take a section through the such a terrace, what you see is that the electric field also rises at an atomic scale compared from the terrace to the edge of the terrace, that is toward the step arcing. So then basically the gas atoms would basically ionize more from high field regions at an atomic scale, and then what they leave on the screen is the impression of this electric field, right? And in some terraces, this electric field is atomically resolved, which enables atomic resolution. And here you can see that each blob basically here would be a surface atom. Right? So field line microscopy in principle is a field ionization of noble gas, and then it gives you a distribution of electric field surface over the sample surface, right? So since I told you that atomic resolution is possible from FIM, we can image one of the most important material defects in FIM, which are vacancies, right? And we could do so in 3 dimensions by also doing a field evaporation of the surface in so-called 3D FIM. And what I present here are 2 results from recent studies, where basically the vacancies were imaged in 3 dimensions. In first case, basically in tungsten, in another case in a nickel-rhenium alloy, wherein there was also an association of vacancies with the added alloying element. However, often posed question is that does the electric field have an influence on these vacancy concentrations? Because sometimes the vacancy concentrations measured from these field line microscopy images are usually higher than the predicted values from the vacancy formation energies. So the question basically, which I would like to answer is, can the high electric field reduce the vacancy formation energy? So in order to do so, what I would do is apply a density functional theory, which can introduce electrostatic fields. And to do that, we use slabs, which can give us experimentally relevant structures. So basically, instead of using a flat surface, we would like to have high Miller index surface, which has a specified step length, specified kink orientation, specified kink length, and also specified terrace orientation. So we have developed this toolbox to give such information and get this high Miller index surface. And then basically you have a surface with steps and kinks. As I said, these would be most relevant sites because this is where the field is concentrated quite a lot. Now, for our DFT calculations, we ensure energy convergence with respect to key point sampling and also plane wave energy cutoffs. And not only that, for electric field calculations, we also ensure convergence with respect to the number of layers which we use. And the electric field which we apply is based on generalized dipole correction method implemented by Christoph et al. In the SFIGS DFT package. Right. So once we have all the recipes ready, then basically what we do is to look for vacancy formation energies. In this case, what we do is we take the surface which we have. Now I'm showing you the XZ slice of this surface. And basically for each configuration, we would place a vacancy starting from the surface, then go to a next configuration where vacancy moves down. So gradually we move the vacancy towards the bulk of the specimen. Then the vacancy formation energy itself is calculated like so, where energy of the configuration containing vacancy minus energy of the slab without any vacancy, and then to this added is the energy of the bulk atom. And this we do with electric field and without electric field. And this I have done for nickel 971 and the platinum 971 surface. And what you see is that basically with electric field, the vacancy formation energy increases compared to when we do not have any electric field, which you can see here. So this, we can already say that it is more difficult to form vacancies in electric field. And if we look closer, why this happens in for example, nickel, what we see is that when we apply an electric field, all the atoms in our slab basically are displaced along the direction of our field application, which is along the Z coordinate. Then based on the displacements of the atoms along the Z coordinate, we can estimate the strain which they undergo, and then basically the Maxwell stress which is acting on our specimen, that would be around 7 gigapascals. And using this strain, basically we can apply this on a bulk cell in the same orientation and strain it, and then introduce a vacancy and calculate vacancy formation energy in the strained bulk cell. And we can do this for a series of strains. And what we end up getting is a curve which looks like this, which shows that in tensile regime, basically we have a vacancy formation energy which is higher, and in compressive regime, then it is lower, right? So it shows that this must be a Maxwell stress interaction with the vacancy's volume, defect excess volume, which is created, and this is what causes the increase in the vacancy formation energy under the application of field. Now, there are some interesting phenomena when we apply electric field. One such thing is for a particular configuration here where the vacancy is just below the surface, but not exactly at the surface, and without any electric field. When we do so, what we see is a vacancy annihilation mechanism, wherein the kink atom basically drops down to the vacancy position. And this happens because it basically retains the same surface configuration. And if we look at the potential energy surface seen by the atom along this path, then basically it has no barrier stopping it from dropping down to the vacancy position, which is here. But once we apply an electric field, this does not happen. And if we look at the barriers, then what we see is that there is an introduction of a barrier to the atomic motion, which happens like this. And this prevents the atom from dropping down to the vacancy position. So in this case, subsurface vacancy is stabilized with help of an electric field. And then we also wanted to see if we have a foreign atom at the kink position, for instance, tantalum, what would be the result? So what we did was to put a tantalum atom now at the kink position. And what we saw that during an application of electric field, what happens is that the step atom next to the tantalum atom then goes and fills the vacancy. This can be easily explained based on the net positive charge attained by each atoms. So in case of pure nickel slab, the net positive charge attained by these step atom is slightly more compared to when we have a tantalum at the king position and nickel at the step position. This is because the nickel's electronegativity is higher compared to the tantalum. It tries to have more electrons, which as a consequence leads to less positive charge on top of this nickel step atom, which prevents it, which leads to lesser stress acting on the atom, and that makes it fall down to the vacancy position. The same is shown by this cross sections through our slabs, where I again show the net charge gain by the atoms, and the position of our step atoms is indicated by this purple arrow. So when we have such a less electronegative atom at the king position, then we can actually also activate vacancy annihilation mechanism even under electric field. So with that, I'm at my conclusions. So what I hopefully was able to show you was that the electric field actually increases the vacancy formation energy. And this, I showed you that this happens because of the defect's excess volume and how it interacts with the tensile nature of the Maxwell stress. So we expect that most of the metals would have a similar trend. So it should be difficult, or the electric field would basically increase the vacancy formation energy. And then we also saw some interesting phenomena which can occur, such as a vacancy annihilation mechanism, which can be activated or inhibited depending on the electric field and the alloying elements, wherein we saw that when we have a pure nickel slab without any electric field, the king atom can go down to the vacancy position, which is prevented when we apply an electric field. Whereas when we have a tantalum atom, then the step atom can fall down this way explained based on the electronegativities of the atoms. So with that, I would like to thank you for your attention, and I leave you with the literature which I have shown throughout. So the current work is available as a preprint, and the relevant literatures are also here. Yeah, thanks. I'm happy to answer any questions or comments.
Great, thanks very much, Jan. That's really interesting work. So I guess the answer to the question is perhaps yes.
There might be other possible mechanisms which I haven't completely ruled out. So it would be a cautious yes.
A cautious yes. Very good. Any questions for Shyam? Richard, please go ahead. Hang on, you're not muted. You're muted still, Richard. Richard, could you please unmute yourself?
Okay, it all seems very plausible to me. In the theory of field evaporation, my story is as follows. When you take an atom off the surface, you create a hole in space. In order to fill that hole with electrostatic field energy, the high voltage generator has to do work. So the field dependence of the bonding energy is actually a field energy term, which is much the same as a field stress term. It's exactly the same, actually. And I suspect there might be a relationship between this story and the one you've just presented.
Yeah, okay.
Any other questions or comments? Okay, well, yeah, thanks very much again, Shyam. I found that really interesting. Our next presenter, Sanba from the University of Rouen. Are you here? Yes. Sanba's talk is going to be on surface dynamics of field evaporation in carbides. Great. Well, we can see your slides, and I could hear you there. So, please, the stage is yours.
Good morning. Do you see my slide?
Yes.
Good. Yeah. Hello, everybody. My name is Samba Njai. I'm doing my PhD in a GPM laboratory. Our interest today will be to assess the influence of surface dynamic of field evaporation in carbide. We are interested in a standard case, which is a silicon carbide with an hexagonal structure. In particular, we know that the silicon carbide is a perfect stoichiometric material. There is 15% of silicon and 15% of carbon. And in the lattice, we may see here that all the first neighbor of carbon is a silicon atoms. This is very important for the following. And for a long time, the presence of molecular ions has been observed on the mass spectrum of silicon carbide. You may see it here. And this is this figure. This is an example in which we have a silicon carbide layer. You may see here the composition is also not perfectly stoichiometric. This is function of the depth. This figure show that in a silicon germanium carbide, we have a dependence of the composition on the Sharp state ratio. So as a field, we see there can be problem of a correct quantification of species in silicon carbide. Similar problems are known in atom probe analysis of compound semiconductor. You may see here, for example, for gallium nitride, you have a decrease of measured fraction of metallic element as function of the field. Here, the fraction of gallium is decreasing in high field, while the nitrogen fraction is increasing. We clearly see here the dependence of the composition as a function of the field. This compositional bias may be due to the detection dead zone. This happened when two ions are too close in time and in space during the detection. So we want to measure the composition, assess and interpret the compositional bias, and then the impact of surface dynamic in the atom probe of silicon carbide. Now we are going to show the result. This is a mass spectrum of silicon carbide tip analyzed by laser atom probe tomography. You may see that the field evaporation of silicon carbide is quite a complex phenomenon because we don't only see silicon and carbon atoms, but we have also a carbon cluster and molecule containing both silicon and carbon. We can understand from this mass spectrum that the chemical reaction from the surface can be happened. If you look now, the density map over the detector area, we can see that the distribution of total amount of silicon and carbon and molecular of silicon carbon 2,2+ form preferentially all in certain regions which are related to the crystallographic structure, so to the field. The crystallographic and the field, so it may play a role in the determination of composition measurement by atom probe tomography. The large amount of molecule appear in the mass spectrum may be due to the fact that the atom may move on the surface of the tip. This have also some consequence on the spatial precision. And the spatial precision, by the way, appear to be very good here in the crystallographic direction as shown by a cross-section here. So in this region, when we zoom in, we can see that the atomic plane are well resolved, but you cannot resolve them if you go a little bit far from the axis pole. The atomic plane are degraded far from this pole because of the degradation of lateral accuracy. At the pole, we see the plane because the contribution of the lateral degradation is 0 here. In this figure, we show the variation of the accuracy of measurement of atoms as a function of the angle of analysis. And we have seen that the resolution, the lateral resolution varies from 1.5 nanometers to 2 nanometers. So the formation of molecules and the loss of spatial resolution give an indication that the atoms may move on the surface. And now we perform a field ion microscopy analysis to see the surface diffusion. The box area in the left video here show one atom's movement on the surface of the tip before evaporating. You can see here by the video here. And the same effect is obtained by applying a laser tip. Here we represent the reconstruction volume of silicon carbide, where the silicon atoms and carbon atoms is shown here. We can see in this figure also that the fraction of carbon and silicon varies with the depth of analysis. So we don't measure the stoichiometric accuracy fraction of carbon and silicon, but what we measure a fraction which is a little bit deviated. This is the same observation for the case of the abundance of a molecular of a carbon 2+, which is very dependent on the depth. Now we can ask ourselves, what is the mechanism of carbon loss? The loss of element should be investigated by a phenomenon called multiple ion detection event. In fact, when we look at the histogram of the multiple event and we discriminate events containing silicon atoms and carbon atoms, it is clear here that the single event here contains more silicon compared to carbon. But when we look the multiple event, we see here that the carbon is in majority. So carbon is mostly found, it is in majority, and the carbon represent 18% of all the multiple events. We can see here that the carbon is found in is mostly found in multiple events, where we have 18%, and the chemistry of carbon is more complex. Then it is more likely that carbon is lost. As a material comparison, we can compare with elemental semiconductor germanium, which we have much lower amount of multiple event, by 2%. Today we will not discuss the origin of the multiple event. We will not discuss the contribution of the dissociation and the contribution of the preferential retention of carbon. And multiple events happened when several atoms are evaporated on the same pulse laser instead of one. You may have also a molecular ion which dissociated during the flight. When the distant impact on the detector is far enough, there is no problem. The detector can detect them, both of them. But when we have multiple events very close each other to the tip, the secondary impact cannot be detected if it is located in the dead region of the first one. The detector is not capable of detecting an ion which are too close in space and in time to the previous one. So the ion will be detected, the first ion will be there and the second ion will be lost. This is possible source of bias on the composition. Now, we lost an ion due to the dead region, but the electric information is not necessarily lost. When two inputs arrive at the same time, the signals are added together. You can see here the amplitude for one ion and the amplitude of for two superposed ions on the detector. I mean that the amplitude change when we have two ions, when two ions arrive at the same time in the detector. In this figure here, you see that we show the amplitude of carbon and silicon. We can see that the signal amplitude of carbon 2+ is higher than that of silicon 2+. This may explain the loss of carbon. And if we compare the amplitude between the beginning and the end of the analysis, we also notice the amplitude increase, notably for silicon. We can also see the difference in this map. This would mean that the loss is more important at the end of the analysis. This is consistent with the evolution of the composition as a function of the depth, what that I have shown previously. In this figure, we show that the multiple events decrease with the depth analysis. This decrease may be related to the fact that some multiple events are transformed into single events due to the extension of the depth region. We may conclude that the best condition is obtained at the beginning of the analysis, where we have a high magnification. And we see that the carbon is much more involved in evaporation of molecular ion and multiple events. And something very important is we see the lattice span at the pole, but the lateral precision is degraded due to the atomic movement on the surface. And we see that the amplitude of the signal can allow us to explore the content of the dead zone. And now the perspective is find a method to estimate the rate of carbon and find an evaporation model that take into account atomic displacement and multiple events. And to improve also the detector performance. It was the talk of Christian Baki. Thank you very much for your attention.
Great, thanks very much, Sandor. Does anyone have any questions? Got time for some questions. I'll start then. So when you showed those thin videos in voltage and laser pulsed mode, and the slight shuffle of some of the bright spots before they left, why do you think that is? Is that a reorganization of the molecule on the surface before it leaves, or does it move? What's your interpretation of that? Oh, you're muted, Summer. You could unmute.
Yeah, yeah, you hear me?
Yes, good.
Yeah. Yeah. Okay. If you apply a field on the tip, the atom move on the surface of the tip. The atom may move on the surface of the tip. It is a case of carbon atoms.
Right. So that's what you think that is, carbon imaging brightly, not related to silicon.
Yeah. Yeah.
Hans-Olaf, you've got your digital hand raised.
Yeah, I just wonder, were you able to check the isotope distribution of the carbon compounds that you found? Because if you look at the 13 carbon, then you can get a measure of how much you lose.
Yeah, I check it, and yeah, I see that the isotope of the carbon 12 is lower than expected compared to the isotope of carbon 13.
Yeah, then you have a measure, and you can do the same thing with the molecular ions also, of course.
Yeah, I can do the same.
If you get some, you should get some little 37 instead of 36 for the 3+, for example, C3, for example, and that should be about 1%, I believe. So you could check all the molecular ions also and make a correction.
Yeah, it is possible to do it, but I am in laser, and in laser, what we have problem. The problem is related to the laser, because we have trend. Yeah, the peak is the mass spectrum is not really a Gaussian shape. The shape of the peak is really, it is not the same with electric. That's why in laser it is difficult to do this kind of correction.
Oh, that's right. Maybe the tail is too big to do this.
Exactly, the tail, I would say.
Yeah.
The tail, yeah.
Okay, well, we're here to get together. So, Nikita, do you want to ask your question? You've got your hand up there.
Yeah.
Yes, very short question, Samba. Very nice talk. Thank you. On slide 12, you showed that the multiples increase towards the end of your measurement, but I would expect them to increase because you said the composition is getting more wrong and wrong. So did I get something wrong, or you said, yes, I would expect the multiples to increase because the composition is more wrong at the end. So how does it go together?
Yeah, this is a very interesting question, because me also at the beginning I thought that the multiple events should increase, and we see that the multiple event is decreasing. This is explanation. The explanation what we have is it is due to the magnification. At the beginning of the analysis, the tip is too sharp and the magnification is too high, because the time of flight is too high also, because we apply less voltage. And at the end of the analysis, the time of flight is too short, and it is more likely that we lose atoms due to that region. Because if the time of flight is short, the magnification is less, and the multiple event is transformed to single event. That's why the multiple event is decreasing with the depth.
Okay.
Yeah.
Okay,
thank you very much.
Great, thank you. So there's another question in the chat there for you, but we'll leave it there. Thank you again.
Thank you.
So our next speaker is Markus Kubach. I can see you there now, Markus. You can share your screen. So Markus comes from the Humboldt Universität in Berlin. His talk is on supporting fair research data management in Atom Probe, an example of coupling cloud computing capable software tools for reproducible data analysis workflows. It rolls straight off the tongue. Great, thanks very much, Markus.
Yeah, thank you very much. Long title, but also pretty much work that has been put together by many people. Can you hear me well?
Yes, we can hear you.
You can also see my slides well. That's nice.
Yes.
Thank you very much. Yeah. Thank you very much, first of all, to the organizers for, in fact, bringing together a fascinating talk, and also thanks so much for having had the chance to give a talk here, and then also having had a chance to enjoy so many fascinating and really nice and high quality talks I've seen. So that was really nice. This work, and I'm really happy to present this work, which we've been putting together with, in fact, many people, and in fact, the good thing is a growing team of people have worked from that connects to a talk from Alokik Saxena that was given yesterday, and also conceptually it connects, I think, very nicely to a talk that Daniel Haley gave on the FAIR session. So, of course, my mouse works. That's great. So, contextualization. So, why are we doing this, and what's the idea behind this? So, some of you might have heard that in Germany, there's now much more funding towards funding science really from the bottom up towards building a research data infrastructure tools, so software tools that allow researchers to store data, to create data schemes that describe better and more completely what the data are. And that should be essentially leading towards a network of connected research infrastructure tools and data repositories, decentralized with many data in that open source, not all of them, but many of them open source, which can then be used by others, and where basically people can share and do research more effectively and more efficiently. And that is a funding initiative in the order of $1 billion. The consortia are driven by bottom up by the scientists, and in fact for material science and the related disciplines of materials engineering, there are 5 consortia. And what I'm talking today is work from a portion of, a very small portion, in fact, of the work that has been happening in these 2 consortia. So FAIR-MAT, that's where I'm working, and NFDI for MATWork, that's where Tillmann and his team are working with Alokik, Sharad, and many others who are now working together. And in this particular project that I'm talking about, we have been teaming up in order to see how these tools that we're building basically at the moment in our work individually, how they can be better connected and better aligned. And it's work in progress. That what I'm showing here, if you find something that is not working or links that really don't show up properly, you're very much welcome to contact us. So there's no need to leave frustrated. If you're interested in learning more about this, then I have the time to present in such a talk. Feel free to reach out. So there are now substantial resources available to do research data management from the bottom up professional with many teams who work full-time on nothing else than research data management. And I think that's also an atom probe damn needed, because if we really think a little bit about how this technique has been really excellently at world-class cutting edge done, when we think about how atom probe is at the moment handled with respect to research data management, and it happens in silos. And that was nicely pointed out yesterday by Daniel Haley. And I think also Daniel Haley's talk nicely pointed out how that additional value can be gained from having these silos internally better organized and using a really cutting edge technology, but also having the silos ultimately coming together. And in fact, and maybe that's the unfortunate side message to take from this, that is somewhat a culture change. But I would like to show you that that this can be rewarding. And even though, of course, success stories are always tricky to get, in particular when projects start, I think that's in the long run something that is ultimately very valuable, because we shouldn't just be doing some science, we should be doing science in an organized manner. I think the talk from Richard Forbes pointed to us very nicely. So what is our aim? We want to formalize computation workflow specifically in this part of the project, specifically in this combination of people from Matrix, so Tillmann's team, and the team that Claudia is leading, and in Humboldt University and Fairmont project, where we in fact have our small portion with atom probe. When we do atom probe, we have to ultimately talk about how do we store data, because data essentially is the resource, software is the microscope. We heard these talks along the conference, but that alone, storing data somehow doesn't make any sense, honestly. Of course, you do it, you know what's contained in your data, but in fact, as soon as you have to communicate to other people, you usually end up in very long discussions. And the question is, how can this be made more efficient? And that is at some point a work towards standardization. And oftentimes then people run out of the room because standardization is a long and tedious process, and it is, in fact. But it's ultimately useful because then we can save work, hopefully in the long run, because that not everybody has to build their tools themselves, but they can take advantage of all the tools. And that has also been nicely pointed out in several talks already. So depending on how you do and model your data schemes, so how you describe what your data formally are, here's an example from that likely all of us know from what I learned is considered in atom probe jargon, the white book of atom probe microscopy. Here you see range files, and these are a perfect example of data modeling schemes. They are a perfect example how they have very early on been used, but also they are a perfect example of how incomplete they are. Because if you think about where do you store explicitly what the charge state of an ion is, yeah, that's a comment here. Yeah, so that's not much happening. And in fact, still fast forward in 2022. Even though this has been proposed very nicely by Miller, and pretty much more work has picked up on this lately, in particular led by the IFAS, the team, Daniel Haley, many other people, me including, also a very large set of people working together. Still, we, I think, in a state where we can still do substantially better, and substantially better means here, first of all, organize ourselves better, come together better, and also, in fact, see something positive in organizing this. And that's why we in the Fairmont project and also in the Matwerk team, we are very much convinced that we need to have one platform, one tool where people can come together and make these discussions at a very low level. So not everybody of us is like super software savvy or programmer. So we need to have really low level tools. And one such tool we have set up is in fact shown here. I give only the screenshot here for the interest of time. Hopefully next year, and hopefully whenever you meet me somewhere in person, ask me, I can show these tools in live to you. I would very much like to do so, but not in a 15-minute talk when you're sitting on a low internet connection. So what I'm doing here, and what has been summarized here under this webpage here, the Fairmont proposal, is in fact a proposal for a data schema not only for atom probe. It is also covering a proposal for electron microscopy and many other techniques, much more than I can bring here in a short minute talk. But what I want to point out is the web page has been designed in such a way that you can really give very low level, positive or negative criticism, all sorts of comments by having a simple Google-like commenting scheme. You just go to service, you log on. It's an open source service. You can just think it's a service that people use that has been used in the journalism community, and then you can basically annotate specifically, okay, Marcus, what you put up there here with the team, I don't like this, or in our specific atom probe, we have a specific instrument, we have 2 lasers, but here only there's possibility to store 1 laser. Can you consider this? And what we're doing then, we're immediately taking this into account in the development pipeline and then update the schema, because for us, these are living objects. And now I can move to what we're doing together with, in fact, a team which worked so far somewhat independently. So some of you who have been with my previous talks might know that I'm doing also software development in Atom for quite a couple of years now. But also this is happening strongly in Düsseldorf also. And what we decided in this particular bridge project between the Mathwerk and the Fairmont was to say, well, can't we just professionalize our software tools towards describing workflows really in a very systematic way? Okay, what are the algorithmic steps that we're doing? What are the data that come in? How are they passed over to different software tools? The example that I'm showing, this is for cobalt-based super alloy. Here you see the microstructure and thermal treatment. I think that is alone, it's to me just a guinea pig. We could pick any possible atom probe, whether it has radioactive atoms, I don't care. In it, it's basically, we have designed these tools around that they work for every possible atom probe data set that you can measure on a machine, as long as you can export it to POS, APOS, or APT files. And the workflow that we want to contrast is here, you do an experiment, you do reconstruction and arranging, and then you have, of course, all possible opportunities. You can go to your favorite software solution, do some GUI analysis. But what we decided to do is, well, why not use the tools like the two from Allokick that you saw yesterday and my tools, and in fact contrast them on the same data set. So in Allokick's case, you do a composition clustering and then some fancy interface reconstruction so that you get basically the interface and the ROIs. And in my case, I do achieve similar things, but with a different algorithmic framework and additional site analysis that are nice to have. And with that, basically, we can run now into the individual analysis. And the advantage of doing this in a well-documented and open way is that you can then really also compare at a single triangle level, at a single region of interest level, how are numbers individually. If you want, you can go as deep as comparing single numbers, as comparing how the ROIs are arranged, doing advanced computation geometry, graph analysis, comparisons, if you want that. I'm not saying that's always needed, as obviously atom probe is working nicely and thriving, as we've seen in many talks. But it's certainly also something that can be very valuable, because as soon as you have set it once up, you can basically play it through for all your analysis. And you communicate it, and you also communicate then what exactly you are doing at different entry levels. And I think that's really the advantage that comes with this. Let's dive into the example. So in Allokick's case, we had the data set, Allokick made the analysis. So what he's doing is, as he explained, you go in a reconstruction, you grid it up, you take the voxels, you cluster them by composition, and then basically you get a picture like this. So you can segment the faces. Still, you have no interfaces, so no meshes are involved here. These are just the voxels. And then Allokick explained yesterday that he has an algorithm for extracting basically where the individual triangles and their vertices are, and these are shown, and you can then basically do a clustering that basically makes these individual identifiable triangles that belong to identifiable microstructural features. And of course, once you're there, pretty much building on much work that Peter Pfeffer has been going and done for, I think, 10 years now, doing it now also in even more professionalized way and documented way, is that we then describe and analyze these results in detail. If you follow the other analysis strategy on exactly the same data set, this basically my tool that I put forward, which is also giving you access to a completely automated, open source, accessible workflow for doing high throughput isosurface delocalization post-processing analysis on atom probe data. That is scalable up to 1 billion ions, what we've shown lately in the paper. Then you get essentially the same results. So I'll flip now. You see basically, I just flipped it aside because I want to show something else. So you see it's exactly basically the same data set, and you get basically the same results. And I think that's the first time that I really see that you can really heads up compare things one-on-one at the individual triangle level. Now, of course, we have also all this documented in other cases, also in my case, we all document this open source, giving access to every single detail of the data, all the delocalization fields, all the geometric primitives. It's totally in HDF5 and it's maintained and kept track of in Jupyter notebooks. And that's basically what I would consider now the state of the art and where we can already be with Atom Probe, using basically a nexus between what is available in the commercial software and what we can then build upon from the commercial software onwards in the post-processing pipelines to really go and do cutting-edge analysis. With that, you can also couple, of course, and do like what I think in microscopy would be called complementary techniques and combinatorial techniques. You can also combine them according to your wishes. Perfect, thank you. You can also combine then according to your desire individual analysis, like here shown sign distance analysis, that basically also incorporates then the proxygram analysis that we've seen in Dieter's talk. That comes basically as a byproduct of our analysis. How can this be made accessible? And I think that's really a key point also to it. In Matwerk, basically, the service that is being used for now is the MyBinder service, which gives people a cutting-edge tool available with which they can run specifically pre-configured Jupyter notebooks online, so then people can just click and play. In the case of Fermat, we went a little bit further with basically building based on what has already been available with the Nomad infrastructure, build a research data, and then we are building this at the moment, a research data management system around all these services. So that is not specific for Atom Probe, and that's also why the so large team is involved in this talk, because that's basically a service that allows you to have a local installation where you have basically a full open source research data management system for not only Atom Probe, electron microscopy, electronic structure calculations, all coming together with then containerized services. And at the moment in this project, we are really working for harmonizing how these tools can better and more consistently, coherently work together. We face also challenges, and challenges specifically when you write scripting, and that goes towards my last slide, is the challenges that we are mostly facing is when we do this now all in a scripted manner. It's really nice that you can have here, it's all happening in Python, as you see. So we are already at the stage that this is all Python and scriptable. So at no point any longer you have to interact with the C++ codes if you don't want to. The point, however, is that might seem frightening because it's much more inelegant as if you were to click a button on a GUI. But the point is, there are tricks, and then these are not really tricks. They are really like systematized strategies to software development, professional software development, to really make these tools easier accessible. And there are 3 issues that we worked on specifically, and this is really where also the credits very strongly goes to the NFDR Matwerk team, Tillmann, Sharat, Mariano, Thomas Hammerschmidt's team, and who is also working in Fermat. He has, in fact, also a bridge role there. Users may find installations of tool difficult. This has been now solved essentially because there's a CondaForge package which are put together for these tools. So basically, you go on a console, you install a CondaForge. It is essentially complete implementation. We're testing this at the moment. So if there's something on the links which doesn't work below, just let us know, and it's expected in some way. But this is in fact what we are currently heavily working on, because this has been in fact, I think, put together 2 weeks ago or so. Workflows currently are scripted in Jupyter They expose many steps, and this is very nice, but it might also be unnecessarily complex when you have many steps that are then shown up in the script. And that's really where the team for Tillmann is working towards, to get all this nicely integrated, slimmed down into simpler commands that can then be executed in Pyron. So Pyron is a professional materials workflow management system that interacts seamlessly with HPC resources. So basically, with writing such a Pyron job and putting this work that we started now into a Pyron job, you can basically then take all the advantage that comes with Pyron, who does then the management on running these simulations on a computer cluster or on your laptop, doesn't matter. but it also then keeps track in the back end, okay, about the provenance and whatnot. Yeah, data provenance in my tool, for instance, is already completely implemented, but this is at the moment quite cumbersome how to really access it and dive down into too many details, and that's really what we're actively working on at the moment. Next steps, of course, are clear: AI tools connecting to the infrastructure. And that is, in fact, gives you my summary slide. I hope I could show you that there's really a good reason now to start embracing fair research data management, because there are very professional tools coming up now, which are not only working for some people, but they are working specifically tailored for specific domains where people can already now take advantage. And I think also the second punchline is, we are doing this for you. All of you know, maybe I might have never sit in front of doing action in an atom probe experiment, but still you can do some impact. And in fact, we are doing this not for us primarily alone, but we're doing this for the community. And that's in fact showing the team, Claudia here with the Fermat team, and many people who have involved in building the infrastructure, from particularly Marek Scheitgen, Tillman and Thomas here with the team, Thomas and Tillman, who work together here, Shara to put together the containers, Alex is all seen, Bat to provide data, and partners, thank you very much. And with that, thank you very much for your attendance and interest, and feel free to reach out. We are really interested to see how these tools can serve you. Thank you very much.
Great, thank you very much, Marcus. I really commend your enthusiasm. It's great to see. Does anyone, we're a little bit over time, but we're in the last session here.
It's okay. I mean, I'm over time, so don't bring up questions. I think we can put them in chat.
No, we'll take one question in case there is one. Does anyone have one question? All right, well, feel free to pop one into the chat. I'm sure Marcus is keen to answer anything, and we'll move on. So our next presenter is James Douglas from Imperial College London. You can bring up your screen now, James. He's going to be talking about atom probe tomography applications for isotopic pigment analysis. So 15 minutes, please, James. I'll give you a 3-minute warning and a 3-pun maximum. All right.
Unfortunately, right. I didn't put any puns into this. I'll have to put them into the paper instead. Can you hear me okay?
Yes.
All good. Cheers. Yep. It should be less than 50 minutes. Don't worry. Cool. Yeah. So I'm James. I'm from Imperial College London. This is some work, preliminary work on isotopic pigment analysis that we've been doing, part of in my spare time. It's something I'm interested in. Oh, let's see if I can actually move my slides forward. There we go. So a little bit of a background into, actually, before I say that, we're going to go through a little bit about isotopes and atom probe, some of the challenges, some of the applications to isotopic analysis that may not have been fully explored yet, and just some preliminary data on what we've done so far in terms of looking at pigments. So when we do atom probe, we're merely interested in composition variations, but sometimes we're interested in isotopes as well, because they give further information. So like in nuclear forensics, nuclear fission products, in burnup in fuels, geology is a big one. The geologists love their isotopes for various forms of dating. And if we like metals, we go to a very basic idea of hydrogen deuterium isotopes. We want to be able to distinguish between those in our atom probe experiments. Cool. What affects isotope analysis in atom probe tomography? Well, isotopes are just peaks. Peaks still need to be identified. Peaks need to be ranged. Materials often have challenging mass spectra. Here's a nice example of some simulated data from Dan Haley's paper back in 2015 of easy, medium, and hard ones for various reasons. So you can have lots of peaks, medium number of peaks, wide peaks with overlapping tails and things. And there's a big variation in how people range things. And this can impact the number of counts for each isotope. If you're trying to do high resolution isotopic analysis, that can really impact it. And there's a well-documented variation between users to users. So going for automated peak fitting is often required for consistent analysis. And once we know that we can extract out the peaks that we want, do we have enough counts for the level of accuracy that we want for looking at isotope ratios? Generally, atom probe doesn't necessarily get as many counts as you say for a analysis technique that's using larger amounts of volume. So what do other techniques use to confirm the isotopic analyses? So standards. So often would use things with stable isotopic ratios to calibrate our analyses. However, as you may well be aware, you will be aware, atom probe sample volumes are very small. They might be variable on the nanoscale, and then people collect things in different ways. They analyze the data in different ways. Round robins have been done to try and to see how people do things differently and whether we can get standards for those. but there's going to be a large sample to variability compared to larger scale techniques, and we still need to do better on that. We've analyzed standard materials with Atom Probe, but this has generally shown that Atom Probe can match existing techniques rather than being the main technique for analysis. But there has been a fair bit of development in improving isotopic analysis with Atom Probe data. I was involved with some work with Fred Meisenkoten and Phil Gopon on the 3432 sulfur system in sulfides in minerals. And we were looking at automated data processing, use of standard materials and minerals, and then simulated mass spectra as well. So what sort of artifacts are present when we want to be analyzing standards? We want to be able to recover known isotopic variations. So if we know what's in there, either in a simulated data set or in a real data set, and we can try and can we recover it in a reproducible manner? We're not just going to fudge the numbers until we get the right answer. So things that can affect your both the composition and your isotopic variation can be multiple hit loss. These are nice examples from Fred again in terms of boron. And if you want to be able to get reliable, reproducible isotopic analyses, at least for uranium and for the sulfur systems, Fred found that we needed to get rid of all the multiple hits. They were causing a lot of problems, using the uncorrected time of flight spectra, and combine that with adaptive peak fitting to be able to reliably extract out the different peaks and be sure that what we've got is most representative and reproducible. And we can also compare it with simulated data sets. So if we put in a known set of isotopic ratios and make it all noisy, make all the peaks horrible shapes, can we extract that out? Because it's almost certainly going to be very nasty in the actual materials. Cool. So now let's go on to an example. So the idea of having a uniform isotopic ratio for an element, we have our periodic tables and we have our ratios, sort of breaks down a bit when you go into localized areas. So if you look at the isotopic variation, in fact, compositional variation for the overall for the rocks you take out, but if you look at isotopic variation of elements in different mines and different minerals, they can give you information about where they come from. White lead, this is going to be linking into the pigments, has been used around the world for pigment for thousands of years. It's very nice, bright and white. And lead mines in Europe have had ore deposits formed through different processes, different isotopic ratios, and you can actually track the ratios depending where the ore came from, where the lead came from. And you can actually see that in the paintings that we're using the lead paint that were made from the ores that came from the mines. So you can actually try and track down where the paint came from and when it was used. And this was done on MCI CPMS, on lead isotopes from old masters paintings. And you can actually track this down. It's quite interesting that you can, in some ways, you can be able to look at it from age if you did the isotopes in that sort of manner, but provenance and trade routes and technology of how these things were processed. And it doesn't just, it's not just for artwork from Europe. This could be anywhere we've got pigments, anywhere we've got glazes, in ceramics. People have been using ceramics throughout human history. And here's an example from 2nd century. This is a portrait of a bearded man. And this was some great work that was carried out by, I think it's at Idaho National Labs. And like all good ideas, if you thought of going, ooh, I want to do this thing, someone else has done it first. So if you want to be able to look at very small amounts of material from your paintings or from your artwork without damaging it, minimally destructive things like TEM or Atom Probe are great, and you can get a great deal of information from a micron scale piece of pigment. And for some reason, the picture that I have of the flake has not come up on there, but it's about 10 microns, 20 microns across. So they're able to extract out a 10, 20 micron piece of material, be able to take a couple of TM lamella, a couple of Atom Probe samples, and they were able to extract out interesting information about the composition. In this case, it was a chromium pigment used that gave it its particular color. They were able to see two different types of the TM, two different types of lead that led them to get information about the processing of these materials. It's all useful. Yes. But the Atom Probe part of this doesn't seem to have been fully explored. And what I'm interested in is, can we look at it for isotope analyses? And you can see here in this data here that they found lots of different elements, and they did find a little bit of lead at the very bottom of the data set. Cool. And just as a bit of a, not background as such, but context for why Atom Probe might be good for this, here's a good example of some of paint on top of the initial white stain. It's initial stain on top of a white lead base for type of paint. And we can see some nice backscattered images of fine and coarse lead white particles. And normally this is in a oil binder. So linseed oil is often one that we use. And then after a while, it reacts with those binders. And the lead particles start to break down, they start to react. You start to form lead soaps, these move around, lead soap aggregates, lead-rich surface regions. And these are some of the processes that happen in paintings with time that lead them to becoming darker, changing in colors. Understanding this is interesting in itself, but also can aid in conservation work. And if you were to look at this sort of image without thinking that it was a piece of paint or something, you go, yeah, I could do atom probe lift out from that region or that region. That'd be quite nice. And be able to get individual samples from the different regions and carry out compositional and isotopic analyses. And that's really where the strength of atom probe come to this sort of work. So what we came out of this was, can we analyze lead particles and lead isotopes in lead white paint using atom probe? So if we want to do this for the first time, well, we're doing it for the first time. I was unable to see much in the literature about this sort of thing. But if you want to do it for the first time, you do a simple baseline material to show viability. You want to be able to make sure that it's as easy as possible. So modern white lead paint, paint it onto an aluminium stub, leave for 6 months, very simple, gold coat it, and then now we can actually see our painted surface over here. Standard fib lift out at room temperature. We're trying to do this as easy as possible. And then in this lift out wedge, you can actually start to see a microstructure. So we can see high atomic number regions and little flakes, and then we can see a lower atomic number matrix, so lower contrast. And that'll be related to the lead carbonate particles and the linseed oil binder. So turn this into a tip. This is half finished. And we did see a bit of beam damage. We could see the tip bend a little bit as we were getting thinner and thinner, at a greater amount than you expect for the base width and for the size of it. So we tried to minimize that as much as possible. And then for the final tip, we were aiming for the higher atomic number regions, the high contrast regions. And we did find, due to difference in milling rates, this is not the nicest of tips. There's a small amount of lumps and stuff on the outside of it, but for the first time, not too bad. Put it in the atom probe, reasonably standard conditions, a little bit warmer than many people will use. It analyzed at relatively low voltages, and we find what you probably expect of a not particularly nice mass spectra, most of it linked probably to the oxidized linseed oil binder. However, we're interested in this stage mainly in the lead, so I'm not too concerned about that at the moment. In the future, certainly, we want to be able to look at these things. And if we look in, we can actually find our lead isotopes, very nice. And as you might expect, it didn't evaporate particularly nicely. But if we're looking for composition and the main sample preparation has given us the site specificity, then it's homogeneous. We're not too concerned with that. We just want to see the isotopes. And that allows us to be able to show that we can actually do this sort of analysis, which is great. So just a bit of a summary. We're able to make atom probe samples of modern white lead paint, lead carbonate, standard room temperature fib lift out. We can see different regions inside the material in this baseline material, and we're able to deliberately put the high atomic number stuff at the top. We can see lead species, although I will say that it wasn't particularly great yield in terms of lead. It was mostly hydrogen, about 200K ions of lead out of a 12 million ion data set, about 20% multiple hits. But we can do it. We can extract out regions that have got lead enriched within the paint, and we can analyze in the atom probe using standard processes before we try and optimize anything. Now, as I said right at the start, if we want to be able to do some sort of isotopic analysis, we need more counts. We can probably, for this material, combine data sets, but we do need more counts to be able to do this. And then once we have more counts, then we can do the extraction of the multiple hits, throw those away, and then we do some peak fitting. But in principle, this seems to be viable. And then what we want to do is similar to what we did for the sulfur system. We want to be able to have a known high and low isotopic ratio. Can we recover that as well? So we have a baseline of modern paint, then we'll have a high and a low. We can do some variations. We can do some comparisons. And then because we had a bit of beam damage and we have a cryofib, the next thing I wanted to do, even though it's a bit more annoying, is to do some cryo sample prep to try and reduce the beam damage, see if it improves the data quality and potentially improves the yield. Anyway, with that, I will say thank you very much, and I think I'm on time.
Well done, thanks, James, very much to time. That's a fascinating image, that one on the top. Calendar winning stuff, I reckon. Has anyone got any questions for James? Well, if you find yourself with a question a little bit later on, pop it into the chat and we'll move on to the last talk. Thanks again, James.
Thank you very much.
Benjamin.
Yes.
Um,
Can you hear me?
Share your screen. So our last talk is given by Benjamin Klaas from the University of War. His talk is going to be on the study of the Santa Catarina meteorite by analytical three-dimensional field ion microscopy. Please, the floor is yours. We can see your slides and hear you clearly.
Okay, so hello everybody. I will present you a study of Santa Catarina meteorite by analytical 3D field ion microscopy. So this meteorite is a metallic meteorite composed by iron and nickel. And this meteorite was remnant pieces of asteroid from 4.5 billion years ago at the dawn of our system solar. This is very interesting because they was cooled at a rate of few degrees per million years, and this very slow cooling allowed to the formation of an ordered phases called tetratinite, and composed of an alternance of iron and nickel plane with very interesting magnetic properties. These magnetic properties was interesting for the study of the electromagnetic field when this body was formed in the solar system, and these phases have also magnetic properties equivalent to war of magnet. So the first study of this meteorite was realized by Müller. And we know there is a two-phase microstructure inside this meteorite. One phase is FCC phases with iron and nickel, and one phase ordered called tetratinite. It's this one that will interest us today because we want to know if this phase have the same orientation in all the meteorites to the study of the paleomagnetic investigation. So basically, FIM works like atom probe, just at the difference, we add inside the chamber an imaging gas to form image that you can see here. This images was resolved at the atomic scale. And if we realize the evaporation in the same time that we realize the ionization of the gas, we obtain sequences of images at different depths inside our sample. These sequences can then use to create these images here called differential images, and on this image we can locate all the atoms to have their position on images. And we can also record the intensity of each pulse. So we obtain this, we call this image space. Basically, it's like position detector in atom probe. And we have also an intensity spectrum where we can differentiate two different chemical species with two different field evaporation. And with this information, we apply a back projection algorithm to reconstruct our tip or our volumes with an atomic resolution and a SOMAR chemical differentiation. Yeah. So to study the Santa Catarina meteorite, first I realized a simulation, a basic simulation with a simple FCC iron matrix, and inside I put some spherical precipitate with the ordered structure with an alternance of iron and nickel plane. All these structures have the same orientation, except this one in the right bottom here with a different orientation. Then I use the Robin-Roland algorithm and the improvements that we realized to obtain FIM images. And we can see on these images precipitates with the ordered structure appear more bright than the matrix because any plane, nickel plane, was brighter than iron plane. experimentally, we observe the same thing, and Miller previously observed exactly the same thing. We have bright plane corresponding to nickel, and we have dark plane corresponding to iron. That means when we will reconstruct with the algorithm that I presented you before our sample, we will not see iron plane because of the contrast on images. So in this slice, inside the reconstruction of one tips, where you see here, or here, for example, some precipitate of the order of phases, we have only nickel plane reconstruct. We cannot see iron planes. And in this precipitate, we also find some defects. We have a zoom here, and these defects correspond to a nickel plane that shift in front of iron plane. We also see this shift on plane on 2D images. Here we have a bright section or bright plane with nickel atoms, and in front of dark section, dark plane with iron atoms. So these defects most likely be an antiphase boundary. And if we look on this sample and other samples that we realize in the same meteorite, we can observe that the superstructure of the precipitate seems to have the same orientation in all the samples, but it's only visual, and we need a tool to characterize this. So to do this, we will use the stereographic Fourier transform. It's basically a stereographic projection of the 3D Fourier transform of our volume. With this, we obtain here a 2D map where we have all the 3D information about the lattice and its orientation in our sample. So this SFT was applied first on the simulated volume, and as you can see, in all the precipitate with the same orientation of the superstructure, we have similar map of SFT, except for this one, where the superstructure is misoriented compared to the other. We have a rotation and a shift inside the SFT map. So if we applied this SFT experimentally, we will see if the superstructure have the same orientation inside all the meteorites. So we do this, and as you can see here on this example, all the superstructure here identified with the here in these images, we have the same orientation. We observed a small shift below 5 degrees, but this shift is due to the reconstruction algorithm less performed at a high angle, and we also see this shift in pure materials. So we can conclude here with this sample and other that we have the ordered phases with the same orientation over a distance of few hundred microns on several tip analyzed. This tip was taken at several hundred microns inside the Santa Catarina meteorite. Then we want to characterize the defect that we observe to be sure that is an antiphase boundary. So a reminder about antiphase boundary here, if we consider this as an iron plane and here a nickel plane, we can constate here the shift that I told you before. But remember, we have on our reconstruction only any plane, nickel plane, so we are in this situation. And if we apply the SFT on this defect, this one, we observed a split inside the 001 spot inside our SFT. If we simulate the same defect if we simulate an APB defect without iron plane, we can clearly observe here the same split on 011 point. We have also more spots here in the SFT because the resolution is better in our simulation. So to conclude, here we can say 3D FIM is allowed to the characterization of the orientation of an ordered structure in materials. In the specific case of Santa Catarina meteorite, we can say the orientation of the superstructure have the same direction on several hundred neutrons. This will help for the understanding of the magnetic properties of these meteorites. And we have also APV defects in these ordered phases that will also involve in the magnetic understanding of this meteorite. So thank you for attention.
Thank you very much. And thank you for keeping to time. Any questions for Benjamin? Nikita.
Hi, Benjamin. Thank you very much for the very interesting talk. I know that the magnetic people are trying to grow this iron nickel LO order structure, and they all failed until now. So my question is, do you have any insights maybe from your measurement on how to synthesize this better, or maybe what insights can you provide for a better synthesis of this material?
So I'm not an expert of the synthesization of this material. I'm not an expert of magnetic properties also. So I just do the analysis to know the orientation inside the meteorites to help people that work on the magnetic properties. So I cannot answer you with a very precise answer here on this topic. Sorry.
Yes, no problem. I was not expecting you precise, but maybe an idea on how to connect this somehow. I don't.
I just know we need to have a very slow cooling to synthesize yes. These phases. I know also there is some thin layer experiment about this, but I do not know more.
There's some creative answers to your question in the chat. Does anyone else have a question? All right, well, we might wrap it up there. So that concludes the last technical session for our conference. I'd like to thank all the presenters again for their contributions. And I'll hand you over to our conference chair. Gang, all yours.
Yes. Thank you also for the chairing this session. All the topics are excellent. Now I think we come to the end of the conference. And I have to confess that we are not professional to run this conference. So please forgive us any imperfections. So secondly, I think when we organize this conference, we have an objective try to make the conference to reflect the frontier development of the technology as well applications. I think this conference achieved this objective. I'm really happy about that. And with these opportunities, I also would like to thank everyone, all the people who join this conference and keep their interest high and make this conference very interesting. I think until the final day, the final talk, I can see, if I look at the people attended still, our 74 people still there. So I hope you all cherish the time in the conference, and I hope the conference gave you a good memory. So that's it. That's what I want to say. Thank you all, and I will leave the final remarks to Francois. Francois there, the president.
Yes, I'm there. You can hear me?
Yes.
Thank you, Gang. So it's my word for the final word for this conference. Okay. My first, I would like to thank Gang for the organization and your team also. You did a wonderful work. I know considering the time scale, that it's a hard work and a very, very good work. So I would like to thank you for that. And so I also want to thank the steering committee member, because we are involved in the organization, in particular our treasurer, so Paul Bagot and Claudia, because as you have seen, we manage the registration. It's not a job we used to do, so it was quite new for us. So it was a bit a mess, but we succeeded at the end. So I would like to thank them for the hard work they did. And I also want to thank my vice president Arun for the organization of the Müller station, which was excellent. We had a very good content. I was so pleased to see young people doing very nice talk and good research, good science. That's really, really nice. And probably I would like to congratulate the winner, Martin Myers. I think he's there. Is Martin there? I don't know.
Yes, thank you very much.
Yeah. Can you open your camera so that you can congratulate you?
Hope that. Let's check the background. Oh, wait.
So congratulations.
Thank you.
It's better like that. It's a pity that we can't congratulate live, so it's my way to do it. Sorry. Thank you
so much.
I also want to thank the poster winner, but I didn't see it in the participant. Is the poster winner there? I don't know.
It's a show down. I'm not sure. Yeah,
no, I'm not sure. Yeah. So congratulations to the winner. So my last thank go to the students that participate to this conference. To this event. I saw excellent work from students. I was so pleased to see that they are able to do good research, considering the time we had the last 3 years without social interaction was terrible for them. And I was happy to see that we're able to manage good research in good science. So it means I'm really pleased that next year we will have our next conference in situ, on site. So they will be able to feel what it is in a real APT&M conference, which is so good. We need social interaction. So I'm so pleased that next year we'll be all together in Belgium. It will be important for us that this conference, which will be together in Rio, because we will have some important business for the society. You probably, since we didn't have any election for the steering committee, because for technical reason and also for legal reason, if you look in the constitution, it was not really clear. So next year we'll have an important business and election, and we could share that together in reality. So thank you again, Gang, and everybody for this excellent conference and excellent organization. It was much light work.
Okay. Yeah. So have a nice weekend, everyone.
Yeah. Have a nice weekend, everybody.
Yeah. Okay. Bye bye. Also welcome you all to come to Nanjing. Yes.
See you later, folks.
Bye bye.